There is a moment, if you have ever stood somewhere truly dark, far from any city, far from any road, where you look up and feel something ancient happen inside your chest. The sky opens, not metaphorically. It opens in a way that the body registers before the mind can translate it. A sudden, vertiginous sense of falling upward into something that has no wall, no ceiling, no end. The stars appear not as points on a flat surface, but as objects at different depths, scattered through a space that keeps going, keeps extending past your ability to follow it with thought. For a moment, standing there, you feel you understand the universe. You feel it is immense but present, full but comprehensible, vast but somehow oriented around the fact that you are looking at it. The stars are there. The sky is thick with them. The whole architecture above you seems constructed from light, from presence, from something that has arranged itself to be witnessed. This feeling is one of the oldest experiences in human history. It is the feeling that produced mythology, navigation, calendar systems, religion, and eventually science. Every civilization that has existed under an open sky has looked up and drawn the same basic conclusion. The universe is something. It is rich, populated, alive with fire and motion. Whatever else it might be, it is not empty. The stars are evidence of a cosmos that has generated and continues to generate an enormous quantity of structure. If you look at any part of the sky long enough, something will be there. A bright star, a cluster, a smear of the Milky Way's spiral arm, and if your eyes are dark adapted, perhaps a faint blur that is not a star at all but a galaxy, an entire second collection of hundreds of billions of stars sitting so far away that its collective light barely crosses the threshold of human perception. The universe seems full. It seems abundant. And this is where we begin, because this feeling, this ancient and entirely sincere impression, turns out to be one of the most profound misreadings in the history of human observation. The universe is not full, not even close. What you see on a clear, dark night is not a sample of what the universe is like. It is a carefully selected exception, a tiny, improbable fraction of what is out there. The stars are real, the galaxies are real. The light arriving in your eyes after traveling for years or centuries or millions of years is real. But what surrounds all of it, what fills the space between every glowing thing, what constitutes the overwhelming majority of what the universe actually contains in terms of volume, is not what you think. And understanding what it really is will change the way this sky looks to you. It will not make it less beautiful, but it will make it something harder to stand under without feeling small in a way that has nothing to do with comfort. And if you want to keep exploring the strange places where science becomes bigger, darker, and harder to explain, subscribe to Beyond the Universe. Because tonight we are not going to look for what fills the cosmos. We are going to follow what it is mostly made of: absence. Let us begin with what we know, with what is measurable, observable, and documented. The observable universe, the region of space from which light has had enough time since the Big Bang to reach us, spans roughly 93 billion light-years across. That number is almost impossible to hold in the mind. 1 light-year is approximately 9.5 trillion kilometers. 93 billion light-years is a volume so large that trying to picture it does not produce an image. It produces a kind of cognitive blankness, a white noise where imagination used to be. But we can try to populate that space. Within the observable universe, astronomers estimate the existence of somewhere between 1 and 2 trillion individual galaxies. Each of those galaxies contains, on average, hundreds of billions of stars. Our own Milky Way is thought to hold somewhere between 100 billion and 400 billion stars. By any terrestrial measure, these are numbers that describe a universe teeming with matter. So when we say the universe is mostly empty, what could that possibly mean? If there are 2 trillion galaxies and each contains hundreds of billions of stars, how can emptiness be the dominant character of the space we inhabit? This is the question that the numbers themselves force us toward, and the answer requires a shift in how we think about scale, because the problem is not counting what exists. The problem is understanding the distances between the things that exist. And those distances are not merely large. They are so enormous that they reframe what the word large even means. Consider the nearest star to our own sun. Proxima Centauri sits about 4.25 light-years away. That means light, traveling at just under 300,000 kilometers every second, takes more than 4 years to cross the distance between our solar system and its nearest stellar neighbor. If you launched a spacecraft at the fastest speed any human-made object has ever traveled, it would take somewhere in the range of 70,000 years to arrive, and Proxima Centauri is the closest one. The next nearest stars are also in the range of 4 to 6 light-years. What this tells us is that even within the Milky Way, A galaxy we think of as our home, our neighborhood, the region we inhabit. The stars are not close together. They are islands separated by almost incomprehensible stretches of open, empty, dark space. But this is still within a galaxy. A galaxy is, by cosmic standards, a high-density region. It is where matter has gathered, compressed, and organized itself into stars and planetary systems and clouds of gas and dust. It is, relative to what lies outside it, crowded. And yet even inside this crowded region, the actual volume occupied by stars and planets and all the solid luminous matter that we associate with the idea of a galaxy is an almost vanishingly small fraction of the total volume the galaxy contains. If you took the Milky Way and compressed all of its stars until they were touching each other, the resulting object would be far, far smaller than the galaxy itself. The galaxy is not a dense object. It is a dispersed collection of extremely isolated objects, separated by distances that make the word isolation sound insufficient. Now take a step back further. Remove yourself from the galaxy entirely. Rise above the disk of the Milky Way until you can see it whole. A luminous spiral shape, 100,000 light-years across. A collection of starlight that from this distance looks like something cohesive, like a single object. Now look around it. In every direction, there is darkness. Not the minor darkness between stars, a different kind of darkness. The darkness between galaxies. The Milky Way's nearest major neighbor, the Andromeda Galaxy, is approximately 2.5 million light-years away. 2.5 million light-years of essentially nothing. Some stray gas, some gravitationally bound dwarf galaxies, some cosmic material, but nothing that could be described as full, nothing that would look like anything from within the gap. The space between the Milky Way and Andromeda is not traversable in any human time frame. It is a silence that has no scale in terrestrial experience. And this is just one neighboring pair of galaxies. Zoom out further. See the local group, the collection of roughly 50 or so galaxies that includes the Milky Way, Andromeda, and their satellites. The local group spans perhaps 10 million light-years. Within that span, dozens of galaxies cluster together under mutual gravitational influence. From outside, it might look like a handful of luminous specks scattered loosely across a dark region. Now zoom out further still. The local group is itself just one small cluster in a larger structure, the Virgo supercluster, which spans something in the region of 100 million light-years and contains thousands of individual galaxies. But even here, even at this scale, the matter is not evenly distributed. The galaxies gather in groups and clusters, and between those groups and clusters there are regions that are largely, deeply, almost completely empty. It gets worse. Zoom out to the largest scales that modern cosmology can map. The full three-dimensional structure of the observable universe as revealed by surveys that have cataloged hundreds of millions of galaxies. And what you see is something that no one who first described it could quite believe. The galaxies are not scattered evenly through space. They are not distributed in any way that suggests uniform filling of a container. They are arranged in a pattern that looks, at its largest scales, like a three-dimensional lattice of thin, branching filaments, sheets, and nodes, and those filaments and sheets and nodes surround, enclose, and define enormous spherical regions that contain almost nothing. These regions are called voids, and it is inside this description that the true character of the universe begins to reveal itself. A void is not simply a gap. A void is not the space between two galaxies the way a hallway is the space between two rooms. A void is a region, hundreds of millions of light-years across in many cases, where the density of matter is so low that essentially no galaxies exist within it, no visible structures, no significant concentrations of anything. The Bode's void, which is among the most studied of these structures, spans approximately 330 million light-years. Stand, conceptually, anywhere inside it, and you are hundreds of millions of light-years from the nearest galaxy in any direction. The darkness inside a cosmic void is not the relative darkness between nearby stars. It is a darkness that has no analogy in anything we experience on Earth. It is a darkness so total, so extended, so structural, that it begins to feel less like an absence and more like a presence. What the large-scale surveys of the universe have confirmed is that these voids are not exceptional. They are not anomalies or statistical accidents. They are the primary feature of the universe at large scales. The filaments and sheets of galaxies, the glowing threads that connect galaxy clusters and superclusters, form a structure that has been named the cosmic web. And the cosmic web is, in a very precise sense, a web built around emptiness. The filaments exist at the edges of voids. The clusters exist at the intersections where several filaments meet. The sheets exist where two voids share a boundary. But the voids themselves, the empty interior regions that the filaments and sheets wrap around and define, occupy the overwhelming majority of space. The structure is not the galaxies. The structure is the pattern of emptiness that the galaxies trace around. This is the inversion that begins to change how the sky feels when you look at it. We are not living in a universe that is filled with matter, with galaxies clustered at different densities with voids as occasional gaps between busy regions. We are living in a universe that is structured around absence. The voids are not what separates the galaxies. The galaxies are what outlines the voids. The lights in the sky are not evidence of fullness. They are the thin, bright margin of something that is predominantly, architecturally, constitutively empty, and this goes deeper than it might initially seem, because the voids are not merely large by the standards we use to describe distance. They are large in a way that challenges our understanding of what the universe was doing when they formed. In the very early universe, matter was distributed nearly uniformly. The cosmic microwave background, the oldest light we can detect, the afterglow of the universe's earliest hot phase, shows us a universe that was almost perfectly smooth. Tiny variations in density existed, fluctuations smaller than 1 part in 100,000, but the overall distribution was remarkably even. And from this near-perfect uniformity, gravity worked on those tiny variations over billions of years, pulling matter toward the slightly denser regions, evacuating the slightly less dense regions, and progressively amplifying the contrast until the universe developed the web-like structure we see today. The voids, in other words, are not spaces where something was removed. They are spaces that matter was pulled out of, drained over billions of years into the gravitational attractors that became filaments and clusters. The voids are the result of the universe's own internal motion, the slow, vast evacuation of space by the force that holds everything else together. Think about that for a moment. Gravity, the force we most associate with binding and holding, with keeping moons around planets, planets around stars, stars within galaxies, has also been the primary driver of the universe's emptying. By pulling matter toward concentrations, gravity has created the enormous evacuated spaces that now define most of the universe's volume. The same force that holds you to the surface of the Earth has been steadily hollowing out the cosmos for billions of years. Structure and emptiness are not opposites in this universe. They are the same process seen from different vantage points. Now, consider what you are, physically, in this context. You are made of atoms. Those atoms are arranged into cells, organs, a body, a mind. Your body occupies a tiny volume on the surface of a rocky planet. That planet orbits a star. That star is one of hundreds of billions within a galaxy. That galaxy is one of trillions within the observable universe. And most of the universe, by volume, by the sheer extent of the space that exists within its boundaries, is void, not merely distant, not merely hard to reach, functionally absent of the material that you are made of. You exist at one of the rarest concentrations of organized matter in a cosmos that, overall, is defined by the near total absence of such organization. If you wanted to describe the universe fairly, accurately, honestly, you would not describe it by talking about the galaxies and the stars and the planets. You would describe it by talking about the vast, structured, evolving emptiness that contains those things in the same way that an ocean contains scattered islands, not as a container barely larger than its contents, as an ocean so enormous that the islands barely register, but it goes deeper. Because the emptiness of space is not simply a matter of distance and void. It extends down through every layer of material reality. You are, right now, composed of atoms, and atoms themselves are almost entirely empty. The nucleus of an atom, where most of its mass is concentrated, is roughly 100,000 times smaller than the atom itself in terms of diameter. If you took a single hydrogen atom and enlarged the nucleus to the size of a marble, the electron's orbital region would extend to the size of a very large building, perhaps a sports stadium. Everything in between, the space that constitutes most of the atom's volume, contains nothing that could be described as solid. The electrons are not tiny marbles orbiting a central marble through empty space in a simple classical sense, but the basic ratio of structure to emptiness within the atom is staggering. The matter you are made of is itself mostly not matter. It is mostly volume, mostly space, mostly nothing in any sense that a macroscopic observer would recognize as something. This layering of emptiness, from the atomic to the stellar to the galactic to the cosmic, is not coincidental. It reflects something fundamental about how physical reality works. Structure forms at specific scales under specific conditions, and outside of those conditions, the default state appears to be absence. The universe is not a container filled with matter that has been arranged into interesting shapes. It is a vast expansion of space in which matter has, in a few places and under particular circumstances, managed to organize itself into the temporary, improbable forms that we call stars, galaxies, planets, and eventually living things. And the scale of what surrounds those organizations, the sheer volumetric dominance of the empty space that those organizations float within, is something that human intuition will never fully metabolize. When you look at the night sky and feel that the universe is full of stars, you are doing something that is understandable, even inevitable. Your brain is not built for these scales. Your visual system evolved to navigate an environment where distances are measured in meters and kilometers, where density is assessed by how many objects you can see in a given visual field, where the presence of light implies the nearby presence of matter. In that environment, a sky full of stars is a sky that genuinely is full. But in the context of what those stars are, where they sit in relation to each other, what proportion of the universe's volume they occupy, the sky you see at night is closer to a nearly blank canvas with a scattering of faint marks than it is to anything resembling a crowded room. And this is before we begin to talk about everything else the universe contains that does not emit any light at all. That conversation is for later, and when it arrives, it will make the visible universe feel even smaller than it already does. For now, hold this. The stars are real, the galaxies are real, the light is real, but the dominant reality of the universe is not the light. It is the dark. Not the dark of nighttime on Earth, which is simply the absence of a nearby sun. The dark of the universe itself. The deep, structured billions of light years across dark of the voids between galaxies. The dark between the filaments of the cosmic web. The dark that has no nearest star. The dark that would still be dark if you traveled through it for longer than the current age of the universe. This is the majority of what the universe is. And learning to hold that fact while still standing on a small, warm planet in the thin, bright margin of an ordinary galaxy is one of the quieter existential adjustments that cosmology asks of anyone who takes it seriously. The night sky that our ancestors looked at, the one that inspired every human tradition that has ever tried to make sense of the heavens, is not a window into the abundance of the cosmos. It is a keyhole, a tiny, improbable aperture through which the light of a few exceptional places manages to reach us across distances that make the word far meaningless. What we see when we look up is the universe's highlight reel, the briefest summary of its most luminous moments, floating against a background of something so dominant, so vast, and so structurally central to everything that, once you truly grasp it, the starlight begins to feel less like fullness and more like a very thin layer of frost on a very dark window. To understand this emptiness more clearly, we have to move beyond the stars themselves and look at the hidden geometry they trace. We have to follow the measurements and maps that revealed where galaxies gather, where they thin out, and where the universe opens into regions so vast and so empty that they seem less like gaps between structures and more like the structures themselves. The cosmic web is not only a story about galaxies, it is a story about the shape of absence and about the strange fact that what glows may be only the outline of what is missing. But before we go there, stay with this image a moment longer. You here now reading or hearing these words exist in a galaxy that is one node on a thin filament of the cosmic web. On one side of you and the other, in every direction that is not toward another filament or cluster, there is a void, a vast, quiet, nearly empty region of space that stretches hundreds of millions of light years before it arrives at the faint suggestion of another filament. The emptiness is not behind the universe. The emptiness is not at the edge. The emptiness is right there, just outside the local concentration of matter that you have the fortune, or perhaps the misfortune, of living inside. It is not approaching. It does not need to. It has been there, surrounding everything you have ever known about the cosmos, since before any star in the Milky Way was born. And it is patient, in the way that only something without a mind and without a boundary can be patient. Permanent, vast, and entirely indifferent to the small fires that cluster at its margins. There is a way of mapping the universe that does not begin with stars. It begins with the positions of galaxies, thousands of them, tens of thousands, eventually hundreds of thousands, each one plotted in three-dimensional space using its distance and direction from us. When astronomers first began doing this in earnest in the latter decades of the 20th century, building what they called redshift surveys, the results that came back were not what most people expected. The expectation, held loosely by many, was that the galaxies would be distributed through space in a way that was roughly uniform, perhaps with some clustering here and there, some denser regions and some sparser ones, but overall a kind of statistical smoothness. Matter spread across the cosmos like grains of sand across a very large floor. What the surveys showed instead was something that required a new vocabulary to describe. The galaxies were not scattered evenly. They were not distributed in any way that resembled randomness at large scales. They were arranged in structures, long, thin chains of galaxies stretching across hundreds of millions of light-years, connected at their ends and intersections to other chains, forming a pattern that branched and looped and interconnected across the entire mapped volume. Between these chains, between these filaments, there were gaps, not small gaps, vast gaps, regions where the galaxy counts dropped to nearly zero, regions that extended in some cases for hundreds of millions of light-years in every direction, regions where the surveys returned almost nothing. The first detailed maps of the large-scale structure showed this so clearly that the researchers who produced them were initially uncertain whether they were looking at a real feature of the universe or some artifact of their method. They were not. The structure was real. The universe at its largest scales does not look like sand on a floor. It looks like the inside of a foam. Foam is an imperfect analogy, but a revealing one. Imagine the bubbles in a foam pressed together, sharing walls with each other, irregular in shape but globally interconnected. Now imagine that the walls of the bubbles are the thin, luminous regions where galaxies exist, and the interiors of the bubbles are the voids, the vast, empty regions that the galaxy walls surround. In this picture, the voids are not holes in the matter. They are the primary units of structure. The matter is the boundary material. The galaxies are clustered at the intersections of bubble walls, along the edges where multiple voids meet, at the nodes where the largest concentrations of matter form the most massive galaxy clusters in the known universe. The voids themselves are the dominant volume. The bubbles are mostly air, and the air is mostly what the cosmos is made of in terms of space. The cosmic web, as this large-scale structure has come to be known, extends across the entirety of the observable universe. It is not a local feature. It is not something specific to the region near the Milky Way. Every large-scale survey that has been conducted, reaching out to billions of light-years in various directions, returns the same basic pattern. Filaments and sheets and nodes of galaxy concentration, separated by and surrounding enormous voids. The universe is structured at its largest scales in a way that places emptiness at the center of its architecture, not as a backdrop or residual space, but as the primary geometric feature around which everything else is organized. One of the things that makes this genuinely difficult to absorb is the time dimension. The cosmic web did not appear fully formed, it evolved. In the earliest moments of the universe, as we noted before, the distribution of matter was nearly smooth. There were density fluctuations, tiny statistical variations in how much matter was packed into any given region, but these fluctuations were minuscule. Over time, gravity worked on them. The slightly denser regions attracted more matter, growing denser still. The slightly less dense regions lost matter to their neighbors, growing emptier still. This process, playing out over billions of years, progressively built up the contrast between the dense regions and the empty ones. The universe's structure deepened over time. The voids grew emptier, the filaments grew denser. The clusters at the nodes accumulated enormous quantities of matter and mass. The cosmic web is not a static pattern. It is the current frame of an ongoing process of structural evolution, and the direction of that evolution has been consistently, relentlessly, toward greater contrast between fullness and emptiness. What this means is that the voids of today are emptier than the voids of 5 billion years ago, which were emptier than the voids of 10 billion years ago, which were emptier than the near-uniform distribution that existed shortly after the Big Bang. The universe is in the process of sorting itself. Matter is concentrating in fewer and fewer places. The spaces between concentrations are becoming larger and more barren. If you could run this process forward far enough into the future, holding only the effects of gravity and ignoring for a moment the other forces we will discuss, you would see the cosmic web become progressively more extreme. The filaments thinning as matter drains from them into the nodes, the voids expanding as the boundary galaxies are pulled into the filaments, the universe's matter becoming ever more concentrated in a shrinking number of massive clusters separated by ever larger and ever emptier voids. But gravity is not the only force shaping this evolution, and this is where the story takes a turn that is, in many ways, more disturbing than anything the voids themselves can offer. Because the universe, it turns out, is not simply a passive arena in which gravity sorts matter. The universe is expanding, not in the sense that the matter within it is flying apart through a pre-existing space. In a deeper sense, the space itself is expanding. The fabric of space-time, the geometric arena in which all the matter and energy of the universe exists, is growing. Every moment, the distance between any two points that are not gravitationally bound to each other increases, not because those points are moving away from each other through space, but because the space between them is becoming more of itself, generating new distance from within. This expansion was not a surprise in the same way that the cosmic web was. The expansion of the universe has been known since the early 20th century, when observations of galaxies showed that their light was systematically shifted toward the red end of the spectrum, the signature of objects moving away from us. Edwin Hubble, whose name most people associate with the Space Telescope, was among those who established this observational fact. The galaxies are receding. The farther away a galaxy is, the faster it is receding. This relationship, known as Hubble's law, confirmed that the universe is expanding uniformly, that any observer anywhere in the cosmos would see the same pattern of recession in every direction. There is no center to this expansion, no point from which everything is flying outward. Every point is equally the center, because every point sees everything else moving away from it. For most of the 20th century, cosmologists assumed that this expansion was slowing down. The reasoning was straightforward. The universe began in an enormous explosion of energy, the Big Bang and gravity, the mutual attraction of all the matter in the universe for all the other matter, should be acting as a brake, pulling everything back, slowing the rate of expansion over time. The question was whether gravity would eventually halt the expansion entirely, causing the universe to recollapse into a singularity, a big crunch, or whether there was enough kinetic energy to expand forever, but at a decreasing rate, eventually approaching some asymptotic stable state. These were the two dominant possibilities. Both assumed that the expansion was decelerating. In 1998, two independent research teams, studying distant supernovae as standard candles for measuring cosmic distances, found something that overturned both scenarios. The expansion of the universe was not slowing down, it was speeding up. The universe was not decelerating under the influence of gravity, it was accelerating. Distant galaxies were receding faster than closer ones, not just because of Hubble's law, but because the rate of expansion itself was increasing over time. Whatever force or phenomenon was driving this acceleration, it was not gravity, at least not the gravity of ordinary matter pulling inward. It was something else, something that acted in opposition to gravity at the largest scales, something that pushed space apart rather than pulling matter together. This something was called dark energy, and of all the uncomfortable facts that modern cosmology has uncovered, this one may carry the most consequential implications for the future. But before we go to dark energy and what it means for the fate of the universe, we need to talk about something that is in some ways even more unsettling in its immediacy, even more fundamental to what the visible universe actually is. We need to talk about dark matter, because even the structure we have described so far, the cosmic web, the filaments, the voids, the clustering of galaxies, cannot be explained purely by the behavior of the matter we can see. There is more, and it does not glow. The first serious evidence for dark matter came not from deep space surveys, but from the rotation of individual galaxies. If you watch a spiral galaxy from the right angle, you can measure how fast its stars are orbiting around the galactic center. Based on the amount of visible matter in the galaxy, the stars, the gas clouds, the dust, you can calculate what the orbital speeds should be at different distances from the center. The prediction follows a straightforward gravitational logic. Stars farther from the center, farther from most of the galaxy's mass, should orbit more slowly, just as the outer planets of our solar system orbit more slowly than the inner ones. This was the expected result. The actual result was different. The orbital speeds of stars in the outer regions of spiral galaxies did not decrease with distance. They stayed roughly constant, or in some cases increased slightly far further out than the visible matter could explain. The rotation curves, as they are called, were flat where they should have been declining. This could mean one of two things. Either the law of gravity worked differently at galactic scales than it does at smaller scales, or there was additional mass in the galaxy that was not visible. A halo of mass surrounding the visible disk, extending far out beyond the luminous region, contributing gravitational influence without emitting or reflecting any light. Decades of observations across different galaxies, galaxy clusters, and cosmological structures have strongly supported the second interpretation. Something is there that we cannot see. Something that has mass, that gravitates, that influences the motion of visible matter, but that does not interact with light in any way that would allow us to detect it directly. This something is called dark matter, and it appears to constitute roughly 27% of the total energy content of the universe. The ordinary matter that makes up everything you can touch, see, measure directly, every atom of every star, planet, gas cloud, and living thing, accounts for only about 5%. Dark matter, invisible and undetected by any instrument except through its gravitational effects, is more than 5 times more abundant. Think about what this means for the picture we have been building. We described the cosmic web, the filaments and sheets and nodes of galaxy concentration wrapped around vast voids. But that description was based on the visible galaxies. The dark matter has its own distribution, and it is not identical to the visible matter, but it is related to it in a fundamental way. Simulations of cosmic structure formation, when they include dark matter, produce results that match the observed cosmic web remarkably well. Without dark matter, those same simulations fail to produce the right structures. The conclusion is that dark matter is not just an add-on to the visible universe. It is the primary gravitational scaffolding upon which the visible universe is built. The filaments of the cosmic web are not filaments of galaxies surrounded by nothing. They are filaments of dark matter within which galaxies have formed. The voids are not simply empty of visible matter. They are regions where dark matter is also sparse, regions that even the invisible scaffolding has largely evacuated as the cosmic web evolved. The galaxy clusters at the nodes of the web are embedded within enormous halos of dark matter that extend far beyond the visible galaxies, holding them together, shaping their dynamics, determining how they will evolve. The universe we see, the universe of stars and galaxies and glowing gas, is like the light showing through the gaps in a structure made of something we cannot see. The architecture is dark. The luminous matter is just the part that happens to glow, and this leads to something more disturbing. If dark matter is the primary structural material of the universe and we cannot see it directly, cannot detect it with any technology we currently possess except through gravitational inference, then what we call the observable universe, the universe we have mapped and measured and described, is only a small part of what is actually there. We are like people in a room who can see the light reflecting off a few objects, but cannot see the walls, the floor, the furniture, the other people. We infer the room from the behavior of what little we can see, but the room itself remains beyond our perception. The universe, even within the bounds of what we call observable, is mostly invisible to us, and this is separate from the voids, separate from the vast empty regions between galaxy filaments. This is invisible matter distributed everywhere, shaping everything, holding everything together, and entirely inaccessible to direct observation. When you look at a photograph of a galaxy cluster, something like the Bullet cluster or the Coma cluster, and see the hundreds of glowing galaxies packed into a relatively small region of sky, you are seeing the luminous minority. The majority of the mass in that cluster and the extended region of space around it is dark matter. It is there in quantities that dwarf the visible galaxies. It permeates the region. It extends in a halo that may be 10 times larger in radius than the visible cluster. It is the dominant gravitational presence, and we cannot see any of it. We know it is there because the galaxies within the cluster are moving too fast to be held together by the visible matter alone. We know it is there because gravitational lensing, the bending of light from more distant objects as it passes through the cluster's gravitational field, reveals mass far in excess of what the luminous matter can account for. We know it is there the way you know there is a wall in a dark room when you reach out and touch it. We feel the presence through indirect effects. We have never held it. We have never seen it. Dark matter does not appear to be made of the same particles that make up ordinary matter. It does not appear to be protons or neutrons or electrons. The leading candidates are various exotic particles that were theorized for other reasons in particle physics, particles that would interact with ordinary matter only through gravity, and possibly through the weak nuclear force, making them almost impossible to detect directly. Enormous underground detectors shielded from cosmic radiation have been searching for dark matter particles for decades. So far, nothing definitive has been found. The detectors grow more sensitive with each generation. The results remain negative. This does not mean dark matter does not exist. The gravitational evidence is overwhelming. It means that whatever dark matter is, it is extraordinarily reluctant to interact with the matter we are made of, which is a remarkable property for something that constitutes more than a quarter of the universe's total energy content. There is a particular philosophical vertigo that comes from sitting with this. You are made of ordinary matter. Your body, the air around you, the planet beneath you, the sun above you, every star in the sky, every galaxy in the visible universe, all of it together, constitutes approximately 5% of what the universe contains in terms of its total energy budget. Everything you have ever directly experienced, every physical sensation, every measurement ever made by a human instrument, Every photon that has ever struck a detector or a retina comes from that 5%. The remaining 95% of the universe, divided between dark matter and dark energy, is accessible to you only through inference, through the behavior of the 5% that you can see, through the ripples and distortions and anomalies that the invisible majority leaves in the visible minority. You are not living in the universe. You are living in a thin, luminous film on the surface of something vastly larger and entirely unknown. And yet this invisible universe is not distant in the way that the Buddha's void is distant, not something that exists in some far-off region of space separated from you by hundreds of millions of light years. It is here, right here, wherever you are. Dark matter permeates the space you inhabit. It flows through the room you are in, through the planet beneath you, through your body, every moment, in quantities that dwarf the ordinary matter you are made of. You have never noticed it, because it does not interact with you in any way you can sense. It passes through you the way a ghost would pass through a wall, if ghosts were real, and walls were mostly empty space, which, as we noted earlier, they essentially are. The dark matter of the universe is not somewhere else. It is everywhere, and its everywhereness is what gives the universe its shape. But dark matter, for all its strangeness, at least has a property we understand: mass. It gravitates, it pulls, it clusters. It is in its behavior, if not its nature, something we can model and predict. Dark energy is something else entirely. Dark energy is the name we have given to the phenomenon or property or substance that is causing the expansion of the universe to accelerate. And in terms of what it actually is, in terms of any physical mechanism that explains its behavior, we are essentially without answers. We know what it does. We do not know what it is. And what it does is extraordinary. In the current cosmological model, dark energy constitutes approximately 68% of the total energy content of the universe, more than 2/3 of everything, more than 12 times the contribution of all the ordinary matter, all the stars and planets and gas and dust that makes up the visible universe. This dominant component of the universe, this thing that outweighs ordinary matter by more than 12 to 1, and dark matter by more than 2 to 1, is the reason the universe is accelerating apart. It is the reason that distant galaxies are not merely moving away from us but are doing so at an increasing rate. It is the reason that the observable universe, the region from which we can in principle receive information, has a boundary that is not simply a consequence of how much time has passed since the Big Bang, but is also a consequence of how quickly space is expanding. The simplest mathematical description of dark energy comes from Einstein's original equations of general relativity, which included a term called the cosmological constant, a term that Einstein himself initially added to produce a static universe, and later, after expansion was discovered, famously called his greatest blunder. It turns out the cosmological constant, or something functionally equivalent to it, may be real after all. In the language of physics, the cosmological constant represents a kind of energy inherent to space itself, a vacuum energy that does not dilute as the universe expands, that remains constant per unit volume even as the total volume of the universe grows. This is deeply strange. As the universe expands and more space comes into existence, more of this energy appears, because it is a property of space rather than of the matter within space. The more space there is, the more dark energy there is, and the more dark energy there is, the faster the expansion accelerates, and the faster the expansion accelerates, the more space comes into existence. The process is self-reinforcing. The universe is not merely expanding, it is expanding in a way that grows more extreme over time, driven by a substance that becomes more dominant the larger the universe gets. Consider what this means in practical terms, in terms of the universe you inhabit and the universe that future observers will inhabit. Right now, the observable universe is enormous, but finite. We can see light from sources up to 46 billion light-years away. The edge of the observable universe defined by how far light has traveled since the Big Bang given the expansion of space. But the universe extends beyond this horizon. There is more universe out there, more matter, more galaxies, more structure, potentially infinite in extent. We simply cannot see it, because light from those regions has not had time to reach us, or because the expansion of space between us and those regions has carried them away faster than light can cross the gap. The observable universe is a bubble, centered on us by observational necessity, bounded not by a physical wall, but by the speed of light and the history of expansion. Now, what happens to this bubble as time goes on and dark energy continues to accelerate the expansion? The answer is both simple and deeply unsettling. The bubble shrinks, not physically, not in terms of the space it contains, but in terms of the information it can receive. As the expansion accelerates, more and more distant galaxies are carried beyond what is called the cosmic event horizon, the boundary beyond which no signal, no light, no information of any kind can ever reach us again. A galaxy that crosses this horizon does not disappear instantly. Its light continues to arrive for some time, red-shifted toward longer and longer wavelengths, dimming and cooling as it goes, until it fades below any possible threshold of detection. But it is gone, in the sense that nothing that happens in that galaxy from that point forward can ever influence us, and nothing we do can ever influence it. It has passed beyond the reachable universe, and it will never come back. This is not a future possibility. It is happening now. Galaxies beyond our cosmic event horizon are already irretrievably beyond us. The event horizon exists right now, at a distance of roughly 16 billion light-years from us, and every galaxy beyond that distance is already separated from us in a permanent and irrevocable sense. The light we currently receive from distant galaxies beyond this horizon is the last light we will ever receive from them, the final messages arriving before the connection is permanently severed. The universe is already in the process of losing parts of itself, already in the process of severing its own internal connections, already in the process of reducing what any given point within it can know about any other. But it goes deeper, because this process does not stop. The expansion continues to accelerate. The event horizon, while it does not shrink indefinitely in simple terms, will over time leave more and more of the currently observable universe beyond the reach of any future observer located where we are. The galaxies that are today just barely within our observable sphere will eventually fade beyond detection, not because they have moved to a physically forbidden location, but because the space between us and them has expanded to the point where their light, even traveling at the maximum possible speed, can no longer close the gap. They will fade, they will redshift, they will cool, and they will be gone. The local group, the collection of gravitationally bound galaxies that includes the Milky Way and Andromeda, will remain. Gravitational binding overrides the expansion for objects that are close enough and massive enough to hold each other. In the far future, the Milky Way and Andromeda are expected to merge, along with several of the smaller local group galaxies, into a single large elliptical structure that some have informally called Milkomeda. This merged entity will persist, holding itself together by gravity, even as the accelerating expansion of the universe carries everything else away. The supercluster we currently inhabit will, over cosmic time, drain its outlying members into this central merged structure, and then sit, a single massive galaxy surrounded by the growing emptiness of an expanding universe from which all other galaxies have long since retreated beyond the horizon. The local merged galaxy, billions of years hence, will look up into a sky that is emptier than ours, not just darker, structurally emptier. The sky will contain the stars of the merged local group and almost nothing else. The vast populations of galaxies that we can currently see, the clusters and superclusters of the cosmic web, will be gone, not destroyed, but removed beyond the event horizon, silent and unreachable. The future astronomers of this distant era, if any exist, will observe a universe that appears to consist of a single galaxy surrounded by void. They will have no way of knowing that the universe beyond the horizon contains more galaxies, more matter, more structure, unless they have inherited records from the past, from a time when the universe was more connected, when the other galaxies were still visible. Our era, the era in which the large-scale structure of the universe is directly observable, is actually a privileged one, and it will not last. This is one of the more quietly devastating implications of dark energy. Not that the universe will end, not that everything will be destroyed, but that the universe will become progressively harder to read, that the evidence necessary to understand its true scale and structure will be carried away by expansion, that future observers, no matter how intelligent or well-equipped, will inherit a smaller-looking universe, one that has erased its own breadcrumbs, and they may not know what they are missing. They may look out at their single apparent galaxy, surrounded by the vast and growing silence of an expanded, cooling, disconnected cosmos, and conclude that this is all there is, that the universe is small and simple and alone, and in a sense, for them, it will be. But we are not there yet. We are here, in the current epoch, still able to see the full complexity of the cosmic web, still able to measure the filaments and voids and clusters and superclusters that constitute the large-scale architecture of the universe. And from this vantage point, with a knowledge of dark matter and dark energy, and the cosmic expansion and the coming isolation, we can begin to ask the question that the rest of this journey is going to explore. What does all of this mean for the long-term trajectory of the universe? What is the universe actually doing at the deepest level, and where is it going? Because the answer to that question is not a continuation of the richness and complexity we see around us. The answer is something that moves in only one direction, and it is the most fundamental direction in all of physics. There is a word in physics that does more philosophical damage than almost any other. It is not a dramatic word. It does not sound like the name of a catastrophe. It sounds almost administrative, almost procedural, like something you might find in the index of a textbook between two more exciting entries. The word is entropy, and if you follow it far enough, if you trace its implications through cosmology and thermodynamics and the deep structure of time itself, it will take you somewhere that makes the voids of the cosmic web feel almost cozy by comparison. Entropy is the reason the universe has a direction. It is the reason time feels like it moves forward rather than backward. It is the reason heat flows from warm objects to cold ones, and not the reverse. And it is the reason that everything complex, everything structured, everything luminous and organized and alive is temporary in a way that is not merely biological or geological but physical, woven into the mathematics of the cosmos at a level from which there is no appeal. The second law of thermodynamics states that in any closed system, entropy tends to increase over time. Entropy, in its most precise formulation, is a measure of the number of possible arrangements a system could be in while still appearing the same at the macroscopic level. A hot, compressed, organized system has low entropy because there are relatively few ways to arrange its components while maintaining those properties. A cool, dispersed, disordered system has high entropy because there are vastly more ways to arrange its components while producing the same diffuse, featureless state. The law says that systems move spontaneously toward higher entropy, toward more disordered, more dispersed, more uniform states. They do not spontaneously move in the other direction. You can warm a room with a fire, but the heat will not spontaneously reconcentrate itself back into a flame after the fire goes out. The process runs in one direction only. This is not a law that applies only to fires and rooms. It applies to everything, to stars and galaxies, and the universe itself. The universe, in its current state, is far from thermodynamic equilibrium. It contains enormous temperature differences, enormous density differences, enormous concentrations of energy in the form of stars burning nuclear fuel and releasing vast quantities of light and heat. These differences are what allow interesting things to happen. Complex chemistry, planetary formation, biological evolution, the generation of structure at every scale, all of these depend on the existence of energy gradients, differences in temperature or pressure or energy density that allow energy to flow. And flowing energy is what drives every process we associate with order, life, and complexity. A universe at perfect thermodynamic equilibrium, where all energy is distributed uniformly and no gradients exist anywhere, is a universe where nothing can happen. It is a universe of maximum entropy, perfectly still, perfectly uniform, perfectly dead. The universe began in an extremely low entropy state. The Big Bang produced an initial configuration of matter and energy that was, paradoxically, highly ordered in thermodynamic terms, not because it was complex or structured in the way we usually associate with order, but because it was so hot and so uniform that the number of ways its components could be rearranged while preserving those properties was comparatively small. From that point forward, the entropy of the universe has been increasing. Stars form from gravitational collapse, releasing energy as light and heat, increasing the overall entropy of the systems they inhabit, even as they represent local pockets of organization. Planetary systems form, and complex chemistry becomes possible in the energy gradient between a hot star and the cold surrounding space. Life emerges as an extraordinarily sophisticated entropy-increasing machine, consuming organized energy and releasing less organized heat into the environment. And all of this is moving in a direction, not toward greater organization, not toward greater complexity as a permanent trend, toward a final state of maximal disorder, maximal uniformity, maximal entropy. The universe, in other words, is burning. Not literally, not all at once, not visibly in every location, but in the deepest thermodynamic sense, it is a system in the process of running down. The energy concentrations that currently drive everything interesting are being spent. The differences that allow processes to occur are being leveled. The organized complexity that we see when we look at the night sky, the stars and galaxies and glowing nebulae, is not a permanent feature of the cosmos. It is a phase, a period in the universe's history when enough of the initial low-entropy endowment of the Big Bang remains unconsumed, that stars can still form and burn and die and form again. But this phase will end. The fuel is finite. The direction is fixed. The entropy of the universe increases, and the universe moves toward a state where that increase slows and eventually ceases, because there is nothing left to increase from. Let us follow this trajectory forward in time, not in the anxious human sense of worrying about what comes next for us or our civilization, but in the cold astronomical sense of asking what the physics actually predicts when we extend the current trends far enough into the future. The timescales involved are not human timescales. They are not even geological timescales. They are cosmological timescales, measured not in millions or billions, but in trillions and quadrillions and numbers that require scientific notation to write. These timescales are as inaccessible to human intuition as the size of the cosmic voids, but they are the natural unit of measurement for the processes we are about to describe. The current age of the universe is approximately 13.8 billion years. The Sun, our star, has been burning for about 4.5 billion years and is expected to continue for another 5 billion years before it exhausts its hydrogen fuel, expands into a red giant, and eventually collapses into a white dwarf. This is a fate common to the vast majority of stars. Most stars in the universe are not like the Sun. Most are smaller, cooler, redder, and far longer lived. The smallest red dwarf stars, with only a fraction of the Sun's mass, burn so slowly and so efficiently that they are expected to remain on the main sequence, fusing hydrogen in their cores, for trillions of years. A red dwarf star might remain stable and luminous for 10 trillion years. Our Sun's total lifespan is less than 1% of that. During this long stellar era, the universe will continue to produce new stars from the gas and dust that remains in galaxies, though the rate of star formation has already been declining for billions of years and will continue to decline. The universe formed stars most vigorously when it was just a few billion years old, a period sometimes called cosmic noon, when the rate of star formation across all galaxies reached its peak. Since then, the rate has been falling. The raw material for star formation, the cold, dense clouds of gas and dust, is being consumed by existing stars and not being replenished in equal measure. Galaxies are running out of fuel. The star-forming regions are fading. The new stars being born today are fewer than those born a billion years ago, and fewer than those will be born a billion years from now. The universe is not in the middle of its stellar history. It is already past the peak. Eventually, on a timescale of something like 100 trillion years, the last star capable of forming from available gas will ignite, burn through its fuel, and fade. The universe will enter what has been called the degenerate era. The stellar era will be over. What remains will be the remnants of the stars that lived and died during the long preceding epoch. White dwarfs, the cooling cores of medium-mass stars like our Sun, which no longer produce energy by fusion but slowly radiate their stored heat into the surrounding space. Neutron stars, the ultra-dense remnants of heavier stars that died in supernova explosions, also cooling, also fading. Black holes, the remnants of the most massive stars, and the supermassive black holes at the centers of galaxies, which neither cool nor fade in the same way but which will eventually face their own fate through a process we will return to. The white dwarfs of this era will be the last widespread sources of light in the universe, but they are not eternal. They cool. Over timescales that can extend to quadrillions of years, a white dwarf radiates away its thermal energy into the surrounding darkness. As it cools, it fades. A hot white dwarf is white or blue-white, emitting significant light and ultraviolet radiation. As it cools, it becomes yellow, then orange, then red, then infrared, then invisible to any detector sensitive only to light. Eventually, in principle, a white dwarf cools to the temperature of the surrounding space, at which point it emits no radiation that carries any significant energy. It has become what physicists call a black dwarf, a cold, dark, inert object the size of a small planet, but containing roughly the mass of a star, floating silently in the expanding, darkening, increasingly empty universe. Here is something that stops the mind for a moment. The timescale for a white dwarf to cool to a black dwarf exceeds the current age of the universe by so much that no black dwarfs are thought to exist yet. The universe is not old enough. The oldest white dwarfs, the first ones to form, have been cooling for billions of years, but they have not had nearly enough time to reach the temperatures at which they would qualify as black dwarfs. In the current epoch, every white dwarf in existence is still warm, still glowing faintly, still radiating the last of its thermal energy at a rate imperceptibly slow by human standards but real. The universe, in its current age, is still young enough that its stellar remnants retain heat. The black dwarf era is something the universe has not yet experienced. It is something waiting in a future so distant that describing it requires the same kind of cognitive surrender we needed for the cosmic voids. But this leads to something more disturbing. In a universe populated primarily by black dwarfs and cooling neutron stars and black holes, floating in an expanding void from which all but the most gravitationally bound structures have long since been carried beyond the horizon, the question of what happens next is not a question about warmth or light or life. It is a question about the stability of matter itself. Because ordinary matter, the protons and neutrons that make up atomic nuclei, and therefore everything you have ever touched or seen or been, may not be truly stable over the very long term. The standard model of particle physics allows for the possibility that protons are not absolutely stable, that over extremely long timescales they can decay into lighter particles through quantum processes. The predicted half-life of a proton, if this decay occurs, is extremely long, perhaps on the order of 10 to the 34th power years, a number so large that writing it in full would require 35 digits. But it is not infinite. If proton decay is real, then on timescales long enough to dwarf even the black dwarf era, the ordinary matter that constitutes black dwarfs, neutron stars, planets, and every atom of every structure that the universe has ever produced will slowly dissolve. Proton by proton, nucleus by nucleus, the complex atomic structures of the material world will break down into their most fundamental components. The black dwarfs will evaporate. The neutron stars will dissolve. Every atom that was ever part of a living thing, part of a planet, part of a star, will eventually cease to be an atom. The matter will not be destroyed in a dramatic sense. It will transition into lighter particles, positrons, and photons, which will themselves eventually scatter into the expanding void. The universe will lose even its cold, dark, inert remnants. It is worth pausing here, not to dramatize this fact, but to sit with it. Everything that has ever been made of protons and neutrons, every piece of chemistry, every cell, every rock, every ocean, every civilization, every artifact, every record, every physical trace of anything that has ever happened in the material universe is, if proton decay is real, ultimately impermanent in a way that has no exception. Not impermanent on a time scale that is merely long, impermanent in the absolute sense. Given enough time, the atoms will not be there. And time in this universe appears to be available in arbitrary quantities. But even if proton decay does not occur, even if protons are truly stable and ordinary matter persists indefinitely, the universe still faces the dominance of black holes. In the very far future, black holes are the last gravitational structures standing. Everything else has either merged into them, been ejected from their host systems by gravitational interactions, or faded into cold remnants. The black holes themselves, seeded from the deaths of massive stars and growing through the accumulation of matter over vast stretches of time, will be the universe's final inhabitants. But even black holes are not permanent. Stephen Hawking, working in the 1970s at the intersection of quantum mechanics and general relativity, showed theoretically that black holes are not perfectly black. They emit a faint thermal radiation, now called Hawking radiation, produced by quantum effects at the event horizon. This radiation carries energy away from the black hole, and because energy and mass are related by Einstein's most famous equation, the mass of the black hole slowly decreases as it radiates. Over an extraordinarily long time, a black hole will lose all of its mass this way, evaporating completely in a final burst of radiation. The timescale for this process depends on the black hole's mass. For stellar mass black holes, the evaporation time is on the order of 10 to the 67th power years. For the supermassive black holes at the centers of galaxies, like the one at the center of the Milky Way, which contains millions of solar masses, the evaporation time extends to perhaps 10 to the 99th power years or longer. These numbers are effectively incomprehensible, but they share one crucial property. They are finite. Every black hole in the universe will eventually evaporate. Every gravitational structure, every concentration of energy, every remnant of every object that has ever existed in the material universe will eventually dissolve through one process or another into a diffuse sea of the most elementary particles and radiation, spreading through an expanding space that is growing ever colder, ever more uniform, ever more devoid of any gradient or difference that could drive a process, produce a structure, or allow a thought. This is the state that physicists call heat death, or the Big Freeze, the final thermodynamic equilibrium of the universe. It is not a dramatic ending. There is no explosion, no sudden catastrophe, no moment at which everything stops. It is an approach, an asymptotic drift toward a condition of maximum entropy from which there is no departure. The universe does not die suddenly. It fades, it cools, it disperses, and then, in the most literal physical sense, there is nothing happening anywhere. No temperature differences to drive a process, no energy concentrations to sustain a reaction, no structures to maintain or collapse, no light to travel between any 2 points, because there are no sources of light, and the photons that were emitted in the final evaporation of the last black holes have long since redshifted to wavelengths longer than the observable universe, and spread across a space so vast that their energy density is indistinguishable from absolute zero. It gets worse, because this heat death is not simply the end of stars and galaxies. It is the end of the conditions necessary for any process that could be called information processing, memory, observation, or experience. Life, as we understand it, requires the flow of energy through organized structures. Thought requires the physical instantiation of patterns in matter and energy. Memory requires stable structures that maintain records over time. All of these require exactly the energy gradients and thermodynamic differences that entropy is relentlessly eliminating. In a universe at heat death, no information can be processed, no memory can be maintained, no observation can be made, because observation itself is a physical process that requires the expenditure of free energy, and free energy will not exist. This means something that is perhaps the most quietly devastating conclusion in all of cosmology. Not only will everything that has ever existed eventually be gone, everything that has ever been known, recorded, or remembered will also eventually be gone. Not because someone destroyed the records, not because a catastrophe erased the archives, but because the physical substrate in which records can exist, the organized matter and energy patterns that constitute storage, is subject to the same thermodynamic decline as everything else. The universe will forget itself, not metaphorically, physically. Every record of every event, every trace of every structure, every echo of every signal that has ever traveled through the cosmos will be dispersed into the uniformity of maximum entropy. Nothing will remain that could be called a record of what happened. Now hold this against what we described earlier about dark energy and the growing isolation of cosmic regions. We said that galaxies beyond our cosmic event horizon are already unreachable, already severed from any future connection with us, already in the process of fading below our detection threshold as the expansion carries them away. We said that future observers in the merged local group galaxy will inherit a universe that looks like a single galaxy surrounded by empty space, with no evidence visible of the vast cosmic web that currently spans the observable universe. But now add the thermodynamic arrow to this picture. Not only will future observers see less because the expansion has removed the other galaxies from view, they will eventually see less and less of even their own galaxy, as the stars in it exhaust their fuel and fade, as the stellar remnants cool and darken, as the black holes evaporate on their unthinkable timescales. The universe will become darker and darker and darker, not just in the sense of the sky becoming more empty, but in the sense of the light that currently exists being progressively extinguished, one source at a time, until the last source is gone. Consider the geometry of this trajectory. Right now, a photon leaving a distant galaxy can travel through the universe and, if the geometry is right, reach a detector somewhere. Information flows. Events in one part of the universe can influence events in another part, at least within the causal boundaries set by the speed of light and the cosmic horizon. The universe is, in its current state, an information-rich environment, full of signals crossing the space between objects, full of light carrying the news of distant events across billions of light years. This will not always be the case. As the expansion accelerates and more regions pass beyond the horizon, the connected volume of the universe, the region from which any given observer can receive information, shrinks. The causal network of the universe, the web of potential influences and signals connecting different parts of space, becomes sparser, more fragmented, more isolated at the level of individual causally connected regions. Eventually, in the far future, even within the gravitationally bound remnant of the merged local group, the flow of information will slow as the energy available to carry signals decreases. The last stars will cool. The communication between the remnants of matter will become progressively more tenuous as the energy to sustain it fades. And in the final epoch, as the last black holes evaporate and the last photons of Hawking radiation spread into the cold, expanding void, the universe will reach a state of almost perfect isolation at every scale. Not just galaxy clusters isolated from each other by the cosmic expansion, but individual atoms, if any remain, isolated from each other by the cooling thermodynamic void. The universe, which began as a hot, dense, extraordinarily connected state, will end as a cold, sparse, utterly disconnected state. Connection was the exception, isolation is the rule, and entropy is the mechanism by which the rule is enforced. There is a thought experiment that sometimes surfaces in discussions of these far futures, a quiet and rather chilling one. Imagine an intelligence, some form of organized information processing, that somehow survived long into the post-stellar era. Not a biological intelligence, not anything made of the chemistry we associate with life, but some hypothetical form of organized complexity that managed to sustain itself on the dwindling energy gradients available in the aging universe. What would such an intelligence know? It would know what it had carried forward from earlier times, what records it had managed to preserve from the era when stars existed and energy was abundant. It would know whatever it had learned from direct observation of its current environment, but its current environment would be growing darker, colder, and less informative with every passing era. The signals available to it would be fewer, the energy available to sustain its processes would be smaller, the universe around it would be growing quieter, and eventually, no matter how sophisticated its methods of conservation and efficiency, the thermodynamic floor would arrive. The last usable energy gradient would be spent, the last process would conclude, and the intelligence would cease, not because it chose to, but because the universe no longer contained the physical conditions necessary for anything to happen. This is not a story about human extinction, though human extinction is implied within it on timescales far shorter than these. This is a story about the universe itself, about what the universe is doing at the deepest level of its physical operation, about what direction all of this complexity and structure and energy is moving in. And the direction is not toward greater richness or greater connection or greater meaning. The direction is toward simplicity, toward uniformity, toward the absence of difference, toward a state so featureless and so still that the word empty, which we used at the beginning to describe the vast voids between galaxy filaments, seems almost too weak to carry the weight of what the universe is ultimately moving toward. The voids between galaxies are empty of structure but still contain space, still contain the quantum fluctuations of the vacuum, still contain the occasional stray particle, and the photons of the cosmic microwave background. The heat death of the universe is emptier than that. It is the absence of anything that could be called an event. And yet, and this is perhaps the strangest and most unsettling aspect of the entire picture, the laws of physics that describe this trajectory are exact, reproducible, tested, and consistent. They are not speculative in the way that speculation about distant civilizations is speculative. The second law of thermodynamics has never been observed to be violated. The expansion of the universe is measured directly. Dark energy's accelerating effect is confirmed by multiple independent lines of evidence. The Hawking radiation argument, while not yet directly observed for black holes, is considered by most physicists to be among the most well-grounded theoretical results at the intersection of quantum mechanics and general relativity. The picture of the universe's far future that emerges from these laws is not a guess or a story. It is a physical inference from principles that currently describe everything we can measure. We are, in other words, not standing outside this trajectory and observing it from a safe distance. We are inside it. The expansion is happening now. The entropy is increasing now. The stars are burning now and spending the fuel that will not be replaced. The galaxies beyond the horizon are fading now, their last light traveling toward us, arriving in our telescopes even as the final connection between us is being severed by the expansion. We exist in a universe that is in the middle of its own slow, majestic, thermodynamic unraveling, and the richness of what we see around us, the complexity and light and connection, is not evidence that the universe is heading somewhere equally rich. It is evidence of where the universe has been. It is the residue of the extraordinarily low entropy state with which everything began, being spent at every moment, irreversibly, in the direction of the silence at the end. The dark matter that shapes the cosmic web is gravitational scaffolding for structures that are temporary. The dark energy that accelerates the expansion is an agent of isolation, separating those temporary structures from each other on timescales that will eventually sever every connection that gravity has not already locked in place. The voids that define the architecture of the universe are growing. The filaments that trace those voids are draining into their nodes. The nodes themselves, the great clusters of galaxies, will eventually be the only gravitationally bound structures in a universe from which everything else has been carried away. And those clusters, over the degenerate era, will lose their stars. accumulate their matter into supermassive black holes and wait, on timescales that make the current age of the universe look like a brief prelude for those black holes to evaporate. And then the waiting will be over, not because something will arrive, but because there will be nothing left to wait. This is the universe, not the universe of the night sky, warm and ancient and full of light, not the universe of the astronomy textbook, rich with nebulae and galaxy clusters and the beautiful imagery of formation and birth. This is the universe of the physics, followed to its actual conclusions, extended across the full length of the time that is available. A universe that began with extraordinary organization and has been moving, every moment since, toward the state of maximum disorganization. A universe that produced, in the middle epoch of its history, an extraordinary variety of complex structures, stars and planets and chemistry and biology, not as endpoints or permanent features, but as transient eddies in the flow of entropy, temporary patterns of organization that the thermodynamic tide is carrying toward dissolution. And the scale of what surrounds those temporary patterns, both spatially and temporally, the voids that dominate the present cosmos, and the silence that dominates the future cosmos, is not a backdrop to the story of those patterns. It is the story. The emptiness is not the frame. The emptiness is the subject. There is a particular quality of silence that belongs only to things that have never made a sound. Not the silence after music ends, which carries the shape of the music within it, a resonant absence that the ear fills from memory. Not the silence of an empty room, which is still populated by the hum of machinery and the distant passage of the world outside. The silence we are describing is something that has no acoustic analog in any human experience, because it is not the absence of sound. It is the absence of the physical conditions that would allow sound, or light, or any signal to exist. It is the silence of a universe that has exhausted every gradient, spent every concentration of energy, dissolved every structure that could vibrate or radiate or interact. It is the silence of a space so cold and so uniform and so empty that the quantum vacuum itself has nothing to fluctuate against. This is where the physics points, and pointing at it changes how everything between here and there looks. But let us not jump to the end prematurely. The journey through time is as important as the destination, and there is much along the way that deserves attention, not because it softens what comes at the conclusion, but because it deepens it. Because the universe, in its slow thermodynamic decline, does not simply dim uniformly like a light on a rheostat being turned down. It dims unevenly, losing its brightest features first while retaining dimmer and dimmer remnants, staging a kind of involuntary retreat from complexity that has its own texture, its own sequence, its own particular way of becoming more and more remote from anything we currently recognize as the universe we inhabit. We are living, cosmologically speaking, in what might be called the golden age of starlight. It will not last. The stars that exist right now, particularly the massive, brilliant ones that produce the most light and heat and drive the most energetic processes in their neighborhoods, are also the shortest lived. A massive star, many times the mass of the sun, may burn through its fuel in only a few million years, a cosmic eye blink. It dies in a supernova explosion, briefly outshining its entire host galaxy, and leaves behind either a neutron star or a black hole. The brightest things in the universe, the blue supergiants and the O-type stars that illuminate vast regions of interstellar space and drive the formation of new stars with their intense radiation, are spending their inheritance rapidly. They are the most extravagant and the most short-lived. The universe's inventory of such stars is being depleted and is not being fully replenished. The medium-mass stars, stars like our sun, burn for billions of years and then die more quietly, expanding and cooling before shedding their outer layers and leaving a white dwarf. They are more economical than the massive stars, but they too are spending their fuel. The small stars, the red dwarfs, burn so slowly that their fuel will last for trillions of years, making them the longest tenured members of the stellar era, but they will also eventually exhaust their hydrogen. Unlike solar mass stars, red dwarfs are thought to be fully convective, meaning they mix their entire hydrogen supply through the burning core rather than exhausting only a central reservoir. This makes them even more efficient, but it does not make them eternal. Even the longest-lived red dwarf will eventually consume its fuel and fade to a cooling remnant. During the long period in which red dwarfs dominate the stellar population of the universe, the character of the cosmos will be very different from what it is today. The sky of a planet orbiting a red dwarf star would be dominated by a dim, reddish sun that provides only a fraction of the light our sun gives us. The universe around it, viewed at night, would be a progressively emptier sky, as the bright blue and white stars of the current era have long since died, and the galaxies beyond the local horizon have faded below detection. It would be a universe recognizable in its basic structure but quieter, darker, more subdued. The same laws, the same physics, the same expanding space. But the ratio of light to darkness would have shifted, the bright exceptions to the universal emptiness having become fewer and dimmer, the darkness having claimed more of the visible territory. Think about what it would mean to do astronomy in such an era. Our understanding of the universe's large-scale structure rests critically on our ability to observe distant galaxies. We map the cosmic web by plotting the positions of galaxies at various distances. We measure the expansion of the universe by observing the redshift of galaxies billions of light-years away. We understand dark energy because we can compare the distances to objects in the early universe with what we expect from a simpler expansion model, and find the discrepancy. All of this requires a universe rich enough in distant observable sources to perform these measurements. In the era of red dwarf dominance, billions of years hence, those distant sources will have faded. The galaxy surveys that allow us to map the cosmic web will not be possible, because most of the galaxies that compose the web will be beyond the event horizon, gone, irretrievable. What remains of astronomical observation will be focused on an ever smaller, ever more isolated local environment, and it goes deeper. We infer the age and history of the universe, partly from the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space. This radiation is currently detectable as a nearly uniform bath of microwave photons at a temperature of approximately 2.7 degrees above absolute zero. But the universe is expanding, and as it expands, this radiation redshifts further. Its photons stretch to longer and longer wavelengths, losing energy, cooling further below the temperature of absolute zero. In the far future, the cosmic microwave background will have redshifted to wavelengths so long and energy so low that it will be, for all practical purposes, undetectable by any instrument that could plausibly be constructed. The echo of the Big Bang will fade below the thermodynamic noise floor of the universe. The oldest and most informative message in the cosmos will become effectively inaudible. This is the erasure we described earlier becoming specific and physical. The evidence for how the universe began, the evidence that allowed us to construct the entire standard cosmological model, will not be preserved forever. It will be diluted by the expansion until it cannot be read. Future civilizations, if they exist in the era of red dwarf stars, might still have records and theories inherited from earlier scientific cultures. But future civilizations in the degenerate era, those hypothetical intelligences we imagined sustaining themselves on dwindling energy gradients, would not be able to reconstruct the history of the universe from direct observation alone. The universe will have overwritten its own autobiography with the blank page of maximum entropy, not destroyed it deliberately, simply allowed the physical processes that carry information to run down until they no longer carry it. There is something in this that sits at the edge of what physics and philosophy share. The question of whether the universe's history has meaning depends, in part, on whether that history can be known. If the events of the past leave traces in the present, if the pattern of what happened is encoded in the current state of matter and radiation and gravitational fields, then there is a sense in which the past persists, in which history is real and recoverable in principle. But if the physical traces of past events are progressively erased by the increase of entropy, if the signatures of what happened are lost to the thermal noise of an aging universe, then the past becomes not merely inaccessible, but, in a physical sense, absent. It existed. It happened, and then it was thermodynamically overwritten. Consider an analogy that is imperfect but suggestive. Imagine writing a message on a piece of paper, then placing that paper in a large sealed room. Over time, the paper degrades, the ink fades, the fibers break down. The molecules that once formed letters disperse into the general chemical environment of the room. The message, which was once clearly present, becomes progressively less readable, then unreadable, then undetectable by any chemical analysis of the room's contents, because the molecules have distributed themselves uniformly through the system. The message was real. It existed. Its existence caused real effects, but those effects have been dispersed and diluted until they are indistinguishable from the background. The room contains the history of the message in some fundamental physical sense. Every molecule that was once ink is still there, but the organization that constituted the message, the arrangement that gave those molecules their meaning, is gone. This is what entropy does to information, and this is what the universe is doing on every scale, to everything that has ever happened within it. Now scale this to the cosmos. Every star that has ever burned has left traces, light traveling through space, gravitational perturbations in surrounding matter, chemical enrichment of the interstellar medium through the elements produced in stellar cores and distributed by stellar winds and supernova explosions. Every civilization that has ever existed, if others have, has left some footprint. Electromagnetic signals traveling outward, physical alterations of local environments, perhaps gravitational signatures of large structures. Every event in the universe's history has a causal shadow, a downstream effect propagating forward in time through the physical state of matter and energy. But all of these shadows are subject to the same thermodynamic dilution. They spread, they mix, they lose their resolution against the background noise of a universe in which the background itself is the dominant feature. The electromagnetic signals of any civilization, even one that has been broadcasting for millions of years, spread as a sphere, and the intensity of that signal decreases with the square of the distance from the source. At cosmological distances, across billions of light years, any such signal would be indistinguishable from the noise floor of the universe. The chemical enrichment of the interstellar medium, the signature of stellar nucleosynthesis, the fingerprint of billions of years of star formation and death, is already mixed and homogenized within and between galaxies by the turbulent processes of the interstellar and intergalactic medium. The physical footprint of any event, no matter how large, is subject to the same spreading and dilution that eventually makes it impossible to reconstruct the event from the footprint. And over the timescales we have been discussing, over trillions and quadrillions of years, the dilution is not partial, it is total. But it gets worse. We have been speaking as if the problem is merely one of signal to noise, of records that exist but are too faint to read. The thermodynamic argument goes further. As entropy increases, the capacity to process information does not merely become harder to exercise, it becomes physically constrained by the available free energy. Computation, in its most fundamental sense, requires the expenditure of free energy. Every logical operation, every bit of information processed, requires energy to perform and releases heat as a byproduct. In a universe approaching heat death, where free energy is vanishingly scarce, the capacity to perform any computation at all is limited by the physical conditions available. The question is not just whether the records exist, but whether any physical system exists that is capable of reading them, which requires its own supply of free energy to operate, which is itself subject to the thermodynamic decline. This creates a picture of the universe's future that is not merely dark in the astronomical sense, but dark in a deeper way. It is a future in which the capacity for anything to know anything progressively diminishes, not because knowledge is inherently impossible, not because the universe is hostile to mind or observation, but because the physical infrastructure of knowing, the organized matter and available energy that constitute the material basis of any process of awareness, is subject to the same entropic decline as everything else. The universe does not become unknowable as a matter of policy. It becomes unknowable as a matter of thermodynamics. And here, at this numbered paragraph, we arrive at what might be the central and most disturbing insight of this entire journey. The universe is not moving toward a state where it is too large to comprehend, too complex to map, too rich to fully understand. It is moving toward a state where it is too empty, too cold, too uniform, too devoid of available energy to sustain the physical processes that constitute comprehension at all. The threat is not vastness. The threat is the specific kind of simplicity that maximum entropy represents. The universe, which has spent 13 billion years producing extraordinary complexity from its initial low-entropy conditions, is in the process of spending that initial endowment completely, irreversibly, and finally. And at the end of that spending, there will be nothing to comprehend and nothing capable of comprehending. The universe will have achieved the purest, most complete form of silence imaginable, a silence not of sound, but of physics. Let us step back from the far future for a moment and return to the present, not to escape the conclusion we have been approaching, but to examine it from a different angle. Because there is something about our position in cosmic time, in this particular era of stellar richness and observable complexity and relative connection, that deserves attention, not as a comfort, but as a fact with implications. We exist in what may be the most observationally favorable era of the universe's history. We can see the cosmic microwave background. We can map the large-scale structure. We can observe galaxies at distances that tell us the history of the universe's expansion. We can detect the signatures of dark matter through gravitational lensing and galactic dynamics. We can measure the acceleration of the expansion and infer the existence of dark energy. We can observe supernovae, quasars, galaxy mergers, the full range of cosmic events that populated the universe's most active stellar era. All of this will not always be possible. We have already established that. The window of observational access to the universe's large-scale structure and deep history is not permanent. It is, on cosmological timescales, brief, and we are living in it. This means something strange about the position of any observer existing now, in this era, who takes the time to look. We are not merely inhabitants of the universe. We are potentially among the most informationally privileged inhabitants the universe will ever produce. Not because we are special in any cosmic sense, not because any process selected for our existence or arranged for our advantage, but simply because of when the accident of our existence occurs. In the current epoch, the universe is readable. Its history is recoverable from its present state. Its structure is mappable. Its past is encoded in light that is still arriving, in radiation that is still detectable, in patterns that have not yet been erased by the advance of entropy. This temporal privilege carries with it a particular weight. Every measurement we make of the cosmic microwave background is a reading of a signal that will eventually fade below detection. Every map of the large-scale structure is a record of an arrangement that expansion will eventually disrupt. Every observation of a distant galaxy is the receipt of a message that, once the expansion severs the connection, will never be replaceable. We are reading the universe's autobiography at a time when it is still legible. Future eras, which may be far longer than our own in terms of absolute time, will have access to less, much less, and the very far future will have access to nothing at all. This is not an argument for urgency in the human sense. The timescales involved are so far beyond any human or civilizational horizon that the word urgent does not apply, but it is an argument for a particular kind of cosmological humility, a recognition that the richness of what we can currently observe is not the permanent background condition of the universe. It is a phase that happens to coincide with our existence, and that we are living inside without, for the most part, recognizing its transience or its depth. When you look at the night sky, even knowing everything we have described, even carrying in mind the voids and the dark matter and the dark energy and the expanding space and the thermodynamic future, the sky still looks the same. The stars are still there. The Milky Way still arches overhead on a clear, dark night. The light still arrives, and this is, perhaps, the strangest fact of all. The universe's trajectory toward darkness and silence and disconnection is invisible on any timescale that has meaning to a human mind. We cannot feel the expansion. We cannot sense the entropy increase. We cannot detect the slow fading of the cosmic microwave background or the recession of distant galaxies beyond the event horizon through any direct perception. The universe looks static and full and present, but it is not static. It is not moving toward fullness. It is moving at every moment in the direction we have described. The stars you see on a clear night are not windows into the universe's future. They are postcards from its past, from a time when the initial low entropy conditions of the Big Bang had been partially but not yet fully spent, when the universe was still rich enough in organized energy to produce and sustain stellar fires on a massive scale. The light from those stars, arriving in your eyes tonight, was produced by nuclear fusion that occurred years or decades or centuries ago. Some of the light from the stars you see has been traveling toward you for longer than human civilization has existed. Some of the objects you see have already died, already faded, already begun the long cooling that will eventually render them invisible, their deaths not yet known to you because the news has not yet arrived. There is a particular kind of loneliness encoded in this, not the loneliness of being isolated from other people, or even the loneliness of being one of a few technologically sophisticated civilizations in a large galaxy. This is a deeper kind, the loneliness of existing in a universe that is, at every moment, becoming less connected, less readable, less able to communicate with itself across the scales of space and time that constitute its full extent. The universe does not experience loneliness. It has no experience. But the structure of what it is doing, the progressive severing of connections between its parts, the progressive erasure of the signals that could in principle carry information between distant regions, the progressive decline in the energy available to sustain any process that could be called communication or awareness, constitutes, in purely physical terms, an objective increase in isolation. The universe is not merely large. It is becoming more alone, and it is doing this not through any external force or catastrophe, but through the ordinary, inevitable operation of the laws that govern it. Dark energy expands the space between galaxies. Entropy disperses the energy within them. Time carries both processes forward without reversal. The cosmic web, which is the universe's most spectacular structure, the most beautiful and complex and surprising arrangement of matter that physics has yet produced, is a temporary pattern in a medium that is inexorably homogenizing. The filaments will drain, the nodes will accumulate and then evaporate, the voids will grow, the horizon will shrink, the background will cool, the remnants will fade, and eventually, across a timescale that makes the current age of the universe look like the first frame of a film that runs for an effectively infinite duration, the universe will approach the condition in which the word structure no longer applies to anything within it. We have been traveling through this landscape from a particular vantage point, looking outward from the present into both the spatial extent of the universe and its temporal depth. But it is worth for a moment reversing the direction, looking not outward but inward, not into the cosmos but into the fact that we, whatever we are, exist here, now, in this specific and temporary configuration of organized matter, in this specific and temporarily favorable era of cosmic history, capable of observing a universe that is in the process of becoming unable to be observed. The coincidence, if that is the word for it, is remarkable, not remarkable in a comforting way. Remarkable in the way that standing at the edge of something very large and very cold is remarkable. The scale of what you are confronting is not hostile, it simply does not care. And the fact that you can recognize it, can follow its implications, can feel the existential weight of it, does not change what it is or what it is doing. There is a question that arises from all of this, a question that the physics does not answer, but that the physics makes unavoidable. If the universe is moving toward a state where no information persists, where no process can occur, where nothing can know or be known, what does it mean that anything ever happened at all? Not in a theological or philosophical sense that requires an answer, but as a structural observation about the relationship between events and their persistence. An event that leaves no trace, that is completely and irreversibly erased by the thermodynamic processes of a universe headed for heat death, is an event that happened, and then, in the fullest physical sense, unhappened, not reversed, not destroyed, but rendered indistinguishable from the background state of a universe in which it did not happen. The stars that burned for billions of years and then faded to black dwarfs, and the black dwarfs that cooled for quadrillions of years and became indistinguishable from the surrounding void, and the protons that decayed on their unthinkable timescales into dispersed elementary particles are not destroyed in any dramatic sense. They are dispersed, they are diluted, they are thermodynamically overwritten. The matter that composed them still exists in some form, somewhere in the expanding universe, but the pattern, the arrangement, the organization that made those atoms into a star, and that star into something that radiated light, and that light into something that crossed space and arrived somewhere, is gone, and the goneness is permanent and total. This is the deepest implication of entropy, and it is the one that sits most heavily on the question with which we began. What if the most disturbing thing about the universe is not what exists inside it, but how much of it is empty, unreachable, invisible, and slowly disappearing from every other part? The emptiness of the cosmic voids is the spatial expression of this. The recession of galaxies beyond the cosmic horizon is the temporal expression of it. The increase of entropy and the eventual heat death of the universe is the thermodynamic expression of it. They are not three separate disturbing facts. They are three aspects of the same fundamental character of the universe, a universe in which connection, structure, and information are the exceptions, always temporary, always subject to processes that work against them, always moving toward dissolution. The universe is not hostile to complexity. It produced extraordinary complexity from its initial conditions, but it is indifferent to complexity in the deepest possible sense. It does not select for the preservation of organized structures. It does not maintain the conditions that allow complexity to persist. It allows complexity to arise where the local conditions permit, in the energy gradients between hot stars and cold space, in the chemistry of planetary atmospheres, in the folded surfaces of biological cells. And then it continues doing what it was always doing, expanding, cooling, increasing entropy, carrying the energy gradients that sustain complexity toward the equilibrium that eliminates them. The complexity was never the point. There is no point. There is only the physics. And the physics says this: the universe began in a state of low entropy and has been increasing entropy ever since. It contains vast regions of empty space that dwarf the regions of organized matter by every measure of volume. It is permeated by invisible dark matter that shapes its visible structures without participating in them in any directly accessible way. It is governed at its largest scales by dark energy, a phenomenon we cannot explain mechanically, that is accelerating the expansion of space and progressively severing the causal connections between its constituent regions. Its stars are temporary. Its galaxies are temporary. Its large-scale structure is temporary in the sense that the expansion will eventually carry all but the most locally bound regions beyond any possible contact. And its capacity to be known, to be observed, to be comprehended, is declining along with the free energy that makes comprehension physically possible. This is not a pessimistic interpretation of the universe. It is not an interpretation at all. It is a description of what the measurements show, extended across the full range of time that the physics implies. The universe is what it is, and what it is turns out to be stranger and emptier and more isolated and more temporary and more indifferent than the night sky suggests. The night sky, which felt so full when we began, which produced in our ancestors that ancient, sincere feeling of a cosmos rich with fire and presence, is a deception not of malice, but of proximity. We are close to the stars. We are inside the galaxy. We are in the luminous margin of the cosmic web. We cannot see the voids from here, not directly, not with unaided eyes. We cannot feel the expansion. We cannot sense the entropy. We see only the highlights, only the bright exceptions to the rule of absence, only the temporary flame in the cold and expanding dark. And yet the flame is real. Whatever else is true about the universe, whatever the physics says about the direction of time and the fate of structure, and the thermodynamic trajectory of everything that exists, the flame is real right now. The stars are burning. The light is crossing the void. The galaxies are moving through their slow, majestic interactions. The complexity is here, present, operating, generating the conditions under which something like an observer can exist and look outward and ask questions about what it sees. This is not a consolation. It is not offered as a reason to feel better about the conclusions we have been drawing. It is simply an additional fact, one that sits alongside all the others without resolving them, without softening them, but also without being erased by them. The universe is moving toward silence, but it has not arrived there yet, and the distance between here and there is itself something that deserves to be understood on its own terms. The question of where we are in the universe's history is not merely academic. It is, in a sense, the most personal cosmological question there is, because it locates not just our position in space, but our position in time, in the arc of a process that had a beginning and will have, if not an ending in the dramatic sense, a state of completion so different from the present that the word continuation loses most of its meaning. We are somewhere in the middle of the stellar era. The first stars formed a few 100 million years after the Big Bang. The last stars, the long-burning red dwarfs, will fade perhaps 100 trillion years from now. Against this total span of the stellar era, we exist near its beginning, roughly 13 billion years in, with something like 100 trillion years remaining before the last stellar light goes out. We are not at the end of the age of stars, but we are also not anywhere near its center. We are in the early chapters of a very long book whose later chapters will be written in progressively dimmer light, and the stellar era itself, vast as it is only the first of several eras in the universe's future, each one longer and darker than the one before. After the stellar era comes the degenerate era, populated by white dwarfs and neutron stars and brown dwarfs and the cold remnants of stellar evolution, lasting perhaps from 10 to the 14th power to 10 to the 40th power years. After the degenerate era comes the black hole era, during which black holes are the dominant surviving structures, lasting until the last supermassive black hole evaporates through Hawking radiation, on a timescale that may extend to 10 to the 100th power years or beyond. And after the black hole era comes whatever state the universe occupies at maximum entropy, a state for which we have mathematical descriptions but no name that carries any emotional weight, because no language evolved to describe it. These eras are not chapters in any meaningful narrative, they are simply the successive states of a system running down. But within the stellar era, within the chapter we inhabit, there are specific events and processes that deserve attention, because they illustrate, in concrete terms, what the universe's trajectory looks like from the inside. One of these is the fate of our own sun, which is not special in any cosmological sense, but which is the closest and most personally relevant example of the stellar processes we have been discussing. The sun is currently a middle-aged main sequence star, converting hydrogen to helium in its core at a rate that has been stable for several billion years and will remain stable for several billion more. But as the hydrogen in the core is progressively depleted, the core will contract and heat, causing the outer layers to expand. The sun will swell into a red giant, growing large enough to potentially engulf the inner planets. This phase will be relatively brief in stellar terms. Then the outer layers will be expelled as a planetary nebula, a shell of gas expanding into the surrounding interstellar medium, beautiful and transient. The core that remains will be a white dwarf, roughly the size of Earth, but containing most of the sun's original mass, hot at first, but cooling steadily over billions and then trillions of years. The planetary nebula that the sun produces will disperse into the interstellar medium over tens of thousands of years, its material becoming part of the general chemical inventory of the galaxy, available in principle to be incorporated into future stars and planets. The elements forged in the sun's core over its lifetime, the helium produced by hydrogen fusion, will add to the galactic pool of helium. The heavier elements in the sun's outer layers will be returned to space. This is the cycle that has been operating for most of the galaxy's history. Stars form from interstellar gas, burn their fuel, return enriched material to the interstellar medium, and that enriched material becomes incorporated into the next generation of stars and planets. Each cycle increases the metallicity of the galaxy, the abundance of elements heavier than hydrogen and helium, making the chemical environment progressively richer in the elements that form rocky planets and complex chemistry, and, eventually, biology. But this cycle is not eternal. It depends on the continuous supply of raw material available for star formation, and that supply is finite and being depleted. The star formation rate of the Milky Way has already declined from its peak, which occurred several billion years ago. The galaxy forms stars today at a rate perhaps 10 times lower than its peak rate. The cold molecular clouds that collapse to form stars are being consumed. The gas returned by dying stars is a partial replenishment, but not a complete one. Some material is locked away in stellar remnants permanently, never returned to the cycle. Some is ejected from the galaxy entirely by supernova explosions and the feedback processes of massive stars. The overall trend is a slow but irreversible decline in the raw material available for star formation, and with it, a decline in the rate at which new stars, new planetary systems, new potential sites for the processes we associate with complexity, are created. The Milky Way will continue forming stars for billions of years, and the red dwarfs that form will burn for trillions. But the era of frequent, vigorous star formation, the era that produced the sun and the conditions for life on Earth, is already past its peak. We are living in the afterglow of the galaxy's most productive period. The stars forming today are fewer than those that formed 5 billion years ago. The stars that will form in 5 billion years will be fewer still. The universe is not in a period of expanding biological opportunity. It is in a period of declining stellar productivity, and that decline, while slow by any human measure, is consistent, directional, and ultimately terminal. This directional quality is worth dwelling on, because it runs counter to an intuition that is almost universal among people who have not thought carefully about cosmological timescales. The intuition is that the universe is still developing, still growing, still becoming something, that the current state of stars and galaxies represents an intermediate phase in a process that is heading toward greater complexity, greater richness, greater diversity of form and structure. This intuition is not unreasonable. On geological timescales, it is roughly accurate. Earth is more complex today than it was a billion years ago, and a billion years ago, it was more complex than it was at its formation. The biosphere has, broadly, increased in complexity over geological time. There is a local planetary trajectory that points toward increasing organization, but this local trajectory exists within a context that is moving in the opposite direction at every larger scale. The galaxy is declining in star formation rate. The universe is increasing in entropy. The cosmic web is evolving toward greater contrast between dense nodes and empty voids, a contrast that will eventually resolve into isolated remnants in an expanding void. The expansion is accelerating, severing connections between regions. These are not trends that will reverse. They are not phases that will give way to something richer. They are the direction of the universe at cosmological scales, and any local increase in complexity, any planetary biosphere or technological civilization, exists not because the universe is heading toward such things, but despite the fact that the universe is heading away from the conditions that allow them. It gets worse in a very specific sense when you consider the relationship between the local and the global. The Earth's biosphere depends on the sun. The sun is a star. Stars are possible because the universe is still in the stellar era, still rich enough in hydrogen gas and gravitational potential to form and sustain fusion reactions. The stellar era is possible because the universe began in a low entropy state and has not yet fully spent that endowment. All of the local complexity, every cell division, every chemical reaction, every thought that has ever occurred on this planet traces back through the chain of physical causation to the initial low entropy conditions of the Big Bang, which provided the free energy that everything since has been spending. The complexity is real, the life is real, the thought is real, but they are all, in the most fundamental sense, derivative of the initial conditions, downstream of the starting state, spending a budget that is finite, and that every process, including the most sophisticated processes of mind and civilization, contributes to depleting. The universe gave us the Big Bang's low entropy. We and the stars and galaxies and everything else that has ever organized itself have been spending that gift ever since, and the spending cannot be undone. Every star that burns increases the entropy of the universe by converting concentrated nuclear energy into dispersed radiation. Every thought that occurs requires the expenditure of free energy and produces heat. Every physical process, without exception, moves the universe one step further along the path toward equilibrium, toward the state where the spending is complete. This is not a tragedy in the narrative sense. There is no tragedy without a subject to experience it. But in terms of the direction of the physics, in terms of what the universe is doing at its deepest level, the movement is irrevocable and the destination is fixed. Let us take one more look at the scale of this, because the scale is where the true weight of it lives. The universe is approximately 93 billion light-years across in its observable extent. It contains something like 1 to 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. The total number of stars in the observable universe is estimated at something like 10 to the 24th power, a number that exceeds the number of grains of sand on all the beaches of Earth by a factor so large it has no useful analog. All of this matter, all of these stars and galaxies and the planets that orbit many of them, all of the chemistry and complexity distributed across this enormous volume, constitutes approximately 5% of the universe's total energy content. The rest is dark matter and dark energy, invisible and inaccessible, and all of it, the visible 5% and the invisible 95%, exists within a structure whose primary feature, by volume, is emptiness. The cosmic voids that dominate the large-scale structure of the universe occupy roughly 80% of its total volume. The filaments and sheets and clusters of the cosmic web occupy the remaining 20%, but within those structures, the actual matter is dispersed across enormous distances, and the matter itself is composed of atoms that are themselves almost entirely empty space. If you could somehow compress all the actual solid matter, all the quarks and electrons that constitute every atom of every star and planet in the observable universe, into a single location, eliminating all the empty space within and between atoms, and all the empty space between stars, and all the empty space between galaxies, and all the cosmic voids, the result would occupy a volume that is almost incomprehensibly small compared to the space it currently inhabits. The universe is not a container that happens to be mostly empty. It is a vast expansion of space in which the presence of matter, at any scale, is the exception so rare that trying to express it as a fraction produces numbers that have no grip on ordinary intuition. And this matter, this tiny exceptional presence in an overwhelming void, is slowly but irreversibly transitioning from organized to disorganized, from complex to simple, from structured to dispersed. The stars are spending the nuclear fuel that was concentrated in their formation. The energy they release disperses into the surrounding space. The complexity that energy gradients allow is temporary. The equilibrium that the dissipation of those gradients approaches is permanent. The voids that currently define the spatial structure of the universe will grow as the expansion carries matter into an ever larger volume. The matter that remains will cool and darken and lose the organized complexity that currently makes it luminous and interesting. The universe, in its totality, is moving from a state in which things happen to a state in which they do not. What does it mean to sit with this? Not to accept it as a belief, not to build a philosophy around it, not to draw any particular conclusion about how to live or what to value, just to sit with the physical description, to hold it clearly in mind, to look at the night sky through the lens of what the measurements and the physics actually say, and to notice what happens. What happens, for many people who follow this far enough, is something that does not have a simple name. It is not despair. Despair requires a sense of personal loss, a feeling that something was owed that will not be delivered. The universe does not owe us anything. It is not failing to deliver on a promise. It is simply doing what it does, governed by laws that have no preference for any particular outcome, moving in the direction that those laws impose, indifferent to the existence of observers who might prefer a different trajectory. It is not nihilism either, or not necessarily. Nihilism implies that nothing has meaning, and the cosmological facts we have described do not, by themselves, determine whether anything has meaning. They describe the physical substrate. They do not prescribe what a mind inhabiting that substrate should or should not value. The fact that the universe is moving toward heat death does not, logically, prevent anything from mattering within the time frame in which it can matter. The flame burns in the cold whether or not the cold is permanent and vast, but it is something. It is an encounter with a scale that is genuinely difficult to absorb, a scale not just of space and time, but of indifference. The universe is not indifferent in the way that a person who ignores you is indifferent, which implies awareness and the choice not to engage. The universe is indifferent in the way that a physical process is indifferent, which is to say that the concept of caring is entirely absent from its operation. The expansion of space carries galaxies beyond the horizon without any awareness that it is doing so. The increase of entropy disperses organized structures without any relationship to the value those structures might represent. The cooling of the universe proceeds without any consultation with the processes that depend on warmth for their continuation. The universe is not cruel. It is not cold in any emotional sense. It is simply operating according to its laws, and those laws produce a trajectory that is, from the perspective of any process that values its own continuation, deeply inhospitable. The night sky that inspired the first human observers, the sky that produced mythology and navigation and calendar systems and eventually the science that has allowed us to understand what it actually is. That sky is a window not into abundance, but into the brief bright margin of a universe defined by absence. The stars are the highlights, the voids are the text, the expansion is the paper, growing larger with every moment, pushing the highlights further apart, making the text harder to read, carrying the whole document toward a uniformity so complete that no future reader, however sophisticated, could reconstruct from it what the document once said. And we are here, in this moment, in this specific sliver of the universe's history, able to read it, able to see the cosmic web and measure the expansion and detect the cosmic microwave background, and infer the existence of dark matter, and understand the implications of dark energy, able to follow the thermodynamic arrow forward in time and understand where it leads, able to look at the night sky and know simultaneously that the light arriving in our eyes is real, and that the darkness surrounding it is the dominant feature of the universe, and that the space between every photon and every source and every distant galaxy is growing, and that the direction of the physics is toward a state in which none of this will be knowable by anything. This is a strange position to be in. It is perhaps the strangest position that anything has ever been in, insofar as we can know. To be a temporary organization of ordinary matter, constituting 5% of a universe that is itself temporary in the thermodynamic sense, located on a thin filament of the cosmic web in the early chapters of the stellar era, capable of understanding the full scope of what surrounds us in space and time and yet entirely unable to alter the direction of any of it. We did not choose to exist in this universe rather than a warmer, more connected, less entropic one. We did not choose to arrive at this point in the arc rather than an earlier or later one. We are here because the physics of this particular universe, unfolding from its particular initial conditions, produced, among its countless other products, the conditions under which we became possible. And the same physics that produced us is carrying us, along with everything else, toward the conditions under which we will not be possible. The night sky looks the same as it always did. The stars are where they were. The Milky Way arches overhead in the same familiar pattern that every human who has ever lived under an open sky has looked up and seen. Nothing about the physical appearance of the sky has changed by virtue of understanding what it means, but what it means has changed. Or rather, what it means has been uncovered, and the uncovering cannot be undone. The sky that once felt full feels different now, not empty in a way that is simply sad, empty in a way that is true, and the truth of it is larger and colder and more final than any myth that was ever told about those stars. There is one more thing worth saying, and it belongs at the end of this journey rather than anywhere else. In all of the vast, cold, thermodynamically declining, expansion-driven, void-dominated universe we have been describing, in all of the dark matter and dark energy and cosmic filaments and bleak far futures and evaporating black holes and approaching heat death, there is one thing that has no clear physical explanation. Not dark matter, whose gravitational effects are well documented even if its nature is unknown. Not dark energy, whose effect on expansion is measured even if its mechanism is opaque. Something else. The fact that any of this is known. The fact that the universe produced, somewhere in its luminous margin, organized matter capable of observing itself and its surroundings and building models of what it sees, and following those models to their conclusions and feeling, genuinely feeling, the weight of what those conclusions imply. Physics does not explain why there is something capable of understanding physics. It does not explain why the laws that govern the universe happen to be legible to the structures those laws produce. It does not explain why the universe, which had no obligation to be comprehensible, is comprehensible. These are not gaps in the physics. They are questions that sit at the boundary where physics ends and something else begins, something for which we do not yet have a satisfying framework. The universe's indifference to its own comprehension, its continuation toward heat death regardless of whether anything understands it or not, is not diminished by the fact of comprehension. But the fact of comprehension is not diminished by the indifference either. Both are real, both are present, and they sit beside each other without resolving, without one canceling the other, in the same way that the starlight and the void sit beside each other in the sky. The universe is mostly empty. What is not empty is mostly invisible. What is visible is mostly temporary. What is temporary is moving, at every moment, toward the state in which it will no longer be. The expansion is accelerating. The horizon is shrinking. The entropy is increasing. The stars are spending. The voids are growing. The connections are being severed. The evidence is fading. And somewhere in the thin, luminous margin of this vast, cold, indifferent, expanding, darkening cosmos, on an ordinary planet around an ordinary star in an ordinary galaxy, in the early chapters of the stellar era, something looked up and noticed that noticing will not last. Nothing lasts, but it is happening now, in the only now that has ever been directly available to anything. The universe does not know it is being observed. The universe does not care. The expansion continues. The entropy increases. The voids deepen. The horizon retreats. And the light from distant stars, carrying the last signals of galaxies already beyond reach, continues to arrive, continues to cross the void, continues to fall on the upturned face of a creature that has somehow learned to read what it means. Not forever, not for long by any cosmological measure, but now, undeniably, irreducibly, now. And in the far future, after the stars have faded and the remnants have cooled and the black holes have evaporated, and the last quantum of Hawking radiation has dispersed into the expanding cold, there will be no record that any of this happened. No trace of the galaxy that once harbored an observer. No echo of the questions that were once asked about the void. No signal, no pattern, no structure carrying the information that anything ever organized itself well enough to look up and wonder. The universe will have achieved its final state, the state it has been moving toward since the first moment of its existence. And in that state, the question of whether anything ever mattered will not be unanswerable. It will be unaskable, because asking requires organization, and organization requires energy gradients, and energy gradients are exactly what maximum entropy eliminates. The question dies not because it is answered. It dies because the conditions that allow questions to exist have been spent, along with everything else, in the irreversible direction of the physics. This is what the universe is doing. This is what it has always been doing from the first moment to the last. Expanding, cooling, increasing entropy, producing, in the middle of its history, a brief, extraordinary complexity that will leave no permanent trace. Moving, without haste and without pause, toward the state of maximum uniformity from which no departure is possible, and in which no departure will be desired, because nothing will exist to desire anything. The silence at the end of the universe is not the silence after sound. It is the silence of the absence of any physical condition under which sound could occur. It is silence all the way down, all the way out, in every direction, across every scale, for every remaining moment of a time that will be, by any measure we can construct, effectively infinite in duration, and absolutely empty of event. Look up. The stars are still there. The light is still real. The void between them is also real, and it is larger, and it is winning. Not now, not in any time frame that touches us directly, but in the only direction that time runs. And the universe does not hurry. It has all the time there is, and it is using it moment by moment to become more of what it fundamentally is: empty, cold, expanding, silent, and entirely, permanently, magnificently indifferent to the brief, improbable, unrepeatable fact that something in its midst once understood what it was, There is a specific kind of knowledge that cannot be unknown, not in the way that a fact can be forgotten, filed away, allowed to fade from active memory until it no longer colors everyday experience. This kind of knowledge changes the structure of perception itself. Once you have genuinely absorbed the scale of the cosmic voids, once you have followed the thermodynamic arrow to its conclusion, once you have understood that the observable universe is a shrinking bubble in an expanding space that is carrying its own contents beyond the reach of any possible observation, you cannot look at a clear night sky and see what you saw before. The stars are the same. The sky is the same. You are different, not because the knowledge is depressing, though it may be, not because it removes wonder, though it transforms it, but because the referent has changed. The sky that once appeared to be background has revealed itself to be foreground. The darkness is not behind the stars are inside the darkness. This inversion is not merely poetic, it is geometrically accurate. The light-emitting matter in the universe, the stars and galaxies and glowing nebulae, occupies a vanishingly small fraction of the total volume. The space between them, the intergalactic voids, the vast featureless expanses of near vacuum that extend for hundreds of millions of light-years between the filaments of the cosmic web, is not the empty container in which the interesting things happen. It is the dominant feature, it is the primary fact. The matter is an interruption in the void, not the other way around. When you look at the night sky and see stars, you are seeing the exceptions. The rule is the blackness between them, and that blackness extends in every direction at every scale, for distances that make the distances between the stars look like the spaces between letters on a page. But even this framing, useful as it is, understates the case, because the voids of the cosmic web, vast as they are still part of the same physical universe as the matter that surrounds them. They are connected, through the topology of space-time, to the filaments and clusters and to every other point in the observable universe. The expansion is carrying all of it apart, yes, but right now, in this epoch, the entire observable universe is still, in principle, causally connected in its history if not in its future. The photons that fill the observable volume, the cosmic microwave background and the light from distant galaxies and the radiation from all the processes that have ever occurred, are all present within this connected region. The void is full of light, even if it is too faint to see, even if the photons are too few and too cold to register on any detector we currently possess. The universe, even in its emptiness, is not devoid of radiation. It is a cold, diffuse, nearly invisible sea of photons stretching across billions of light years. What will the universe look like when that sea of photons has itself been diluted beyond any possible detection? When the expansion has stretched the wavelengths of even the most energetic photons currently crossing the void into wavelengths longer than any scale we can meaningfully describe? The answer is not dramatic. There will be no moment of sudden darkness, no switch thrown, no clear before and after. It will be an asymptotic approach, a forever dimming that approaches zero without ever quite arriving, in the way that mathematical limits approach their values without necessarily reaching them in finite time. But the practical result, across any timescale that could be called observation, is darkness. Cold so complete that the residual radiation of the universe is indistinguishable from the ground state of whatever spacetime is when it contains nothing. A silence that is not the absence of sound, but the absence of the physical conditions under which the distinction between sound and silence would have any meaning. And here's the thing about that final state that most accounts leave unexamined. It does not feel like an ending. It does not feel like anything. That is not a statement about psychology or emotion. It is a statement about the physics. An ending, in any sense that carries weight, requires a subject for whom the ending is an ending, a perspective from which the cessation of something represents the loss of something. The heat death of the universe does not have a subject. There is no point of view from which the final uniformity of maximum entropy represents a conclusion or a loss, or even a fact, because a fact requires a system capable of representing it, and such systems require free energy, and free energy is exactly what maximum entropy eliminates. The universe does not experience its own heat death. It simply arrives at it, the way water arrives at the level of the surface it is poured onto, without knowing it has arrived, without there being any knowing of any kind. This is, in a very specific sense, the most unsettling aspect of the whole picture. Not that the universe ends, not that everything is temporary, but that the ending has no witness. The most profound transformation that the universe will ever undergo, the transition from a state in which events occur to a state in which they do not, will go completely unobserved. Not unobserved in the sense that cameras were not running. Unobserved in the sense that observation will be physically impossible. The universe will complete its thermodynamic trajectory in perfect privacy. No perspective will record the final moment. No instrument will detect the last event. The universe will close without any form of closure, without any audience, without any acknowledgement that it happened at all. Compare this to how it began. The Big Bang, whatever it actually was at its physical core, was an event of extraordinary energy density, a state so hot and dense that the physics we use to describe the current universe breaks down before it can reach that moment. We cannot see the Big Bang directly. The cosmic microwave background, the oldest light we can observe, comes from when the universe was approximately 380,000 years old, already enormously cooled from its initial state. The first moments are hidden behind an opaque wall of hot plasma. In this sense, the beginning is also without a witness. No observer could have existed in the first instance. The conditions were incompatible with the organized structures that observation requires. The universe began without anyone watching, and it will end without anyone watching. And in between, in the thin, bright middle, there was a period in which something organized enough to observe existed and looked and wondered. That middle period is what we are inside. Its duration, measured against the full timeline of the universe from the Big Bang to the heat death, is genuinely difficult to place in proportion. The stellar era, the period during which stars can form and burn, spans perhaps 100 trillion years. The degenerate era that follows spans longer. The black hole era spans longer still. The approach to maximum entropy is, for practical purposes, indefinitely long. Against this total timeline, the period during which biological complexity is possible, which requires liquid water and stable energy sources, and the chemical richness produced by stellar nucleosynthesis and planetary geology, is brief, vanishingly brief. A thin sliver in the early part of the stellar era, constrained at its beginning by the time required to produce heavy elements through stellar evolution, and at its end by the increasing scarcity of star-forming material and the eventual expansion-driven isolation of all remaining structures. We do not know how long this sliver extends. We do not know whether the conditions for biological complexity exist elsewhere in the universe right now, whether other planets harbor other forms of chemistry complex enough to observe and reflect. We do not know whether such complexity is common or rare, whether the universe is populated by observers or whether we are, improbably, nearly alone in the luminous margin of the cosmic web. The question of extraterrestrial life is one of the most consequential open questions in science, and the honest answer is that we do not know. The universe is old enough and large enough that the emergence of life elsewhere would not be surprising by any probabilistic argument. The absence of clear evidence for it is a fact about the limits of our detection rather than a definitive conclusion about its presence or absence. But here is what is true regardless of whether the universe contains one observer or a billion. The laws of thermodynamics apply everywhere equally. The expansion of space affects every region of the universe that is not locally bound by gravity. The entropy increase is universal, not local. The approach to heat death is the trajectory of the entire system, not just the part we inhabit. Any observer anywhere in the universe bound by the same physics we are bound by faces the same cosmological context, the same growing voids, the same accelerating expansion, the same thermodynamic arrow, the same ultimate destination of maximum entropy. The question of whether we are alone is a question about the distribution of a rare property within a universal context. It does not change the context, and the context is this. The universe is a physical system that began in a low entropy state, has been increasing entropy ever since, and will continue to do so until it reaches the maximum possible entropy compatible with its evolving volume and energy content. Along the way, it has produced structures of extraordinary complexity, stars and galaxies and chemistry and possibly life and possibly mind, as local, temporary exceptions to the overall trend toward uniformity. These exceptions do not alter the trend. They are expressions of it, ways in which the entropy of the system increases by routing the dissipation of free energy through organized structures rather than through simple thermal radiation. You are one of these organized structures. Your existence is a route by which the universe converts organized energy into dispersed heat, a physically inevitable process temporarily taking the form of a mind. This is not meant to be reductive. The fact that you are a thermodynamic process does not mean you are only a thermodynamic process, any more than the fact that a symphony is a pattern of air pressure variations means it is only a pattern of air pressure variations. The description at the physical level is accurate. It is not complete in the sense that it does not capture everything that is true about what it describes, but the physical description is real, and it does not go away when you add other descriptions to it. You are temporary. You are made of atoms that are mostly empty space. You are a local eddy of low entropy in a universe that is overall increasing entropy. Your existence depends on the continued burning of a star that is spending its irreplaceable fuel, and the universe that contains you is moving at every scale and in every direction toward the conditions under which nothing like you will be possible. There is something here that sits beyond the reach of both comfort and despair, something that does not resolve into a feeling that can be named and filed. It is the sensation, if that is the word, of genuine scale, not the scale of large numbers or large distances, which can be memorized and repeated without really landing. The scale of context, the context in which everything you have ever experienced, every sensation and thought and memory and relationship and moment of beauty or grief, exists as a feature of a universe that has no awareness of it, no preference for its continuation, no structure that ensures its preservation. The context in which the entire history of life on Earth, from the first self-replicating molecules to whatever comes after us, occupies a period smaller than a rounding error in the timeline of the stellar era. The context in which the stellar era itself is a brief opening act before the long darkness of the degenerate and black hole eras, which are themselves brief preludes to the effectively infinite approach to heat death. The mind does something interesting when it tries to hold this context. It tends to bounce off it, to accept it intellectually while continuing to operate as if the human scale is the relevant scale, because the human scale is the only scale at which living is actually possible. You cannot live at cosmological scale. You cannot feel the expansion of the universe in your daily experience. You cannot perceive the entropy increase in the background radiation. You cannot observe the recession of galaxies beyond the horizon in any way that changes how you move through your day. The physics is real, but it is not operationally present in the way that hunger or cold or the face of another person is present. The cosmological context does not override the human context. It surrounds it, and perhaps this is the right way to hold it. Not as a correction to the human scale, not as a demonstration that the human scale is an illusion or a mistake, but as an additional fact about the full structure of what exists. The human scale is real. The stars are real. The voids between the galaxies are real. The thermodynamic future of the universe is real. These are all true at the same time, descriptions of the same thing at different resolutions, and none of them cancels the others. The fact that the universe is mostly empty does not make the people in it empty. The fact that everything is temporary does not make anything valueless, unless value requires permanence, which is a requirement that value was never given and never claimed. The fact that entropy is increasing does not mean nothing is organized. It means the organization is temporary, which was always true, even before we knew the physics. But there is something the physics does to the question of significance, not by answering it, by reframing it in a way that makes the usual answers feel insufficient. The usual answers to questions of significance are constructed at the human scale, rooted in relationships and purposes and contributions to things larger than oneself, legacies and communities, and the ongoing project of civilizations that will outlast any individual. These answers are real. They are not rendered false by the cosmological context, but they are also not insulated from it. A legacy that outlasts a person is still subject to the thermodynamic decline that will eventually erase all legacies. A civilization that persists for thousands of years is still a feature of the brief luminous margin of the stellar era. The things we build, the meanings we construct, the values we live by all exist in a universe that will, in the fullness of its time, dissolve them as thoroughly as it will dissolve the stars. This is not nihilism, but it is a fact that sits adjacent to nihilism, close enough that distinguishing the two requires care. The distinction is this: nihilism says nothing matters. The cosmological picture says everything that matters within a context of ultimate impermanence. These are not the same claim. The first is a statement about value. The second is a statement about duration. Duration and value are not the same thing, and conflating them, feeling that impermanence implies meaninglessness, is a philosophical move, not a logical necessity. The universe does not confirm nihilism. It simply declines to confirm the alternative. It offers no evidence that things matter. It offers no evidence that they do not. It offers physics, and leaves the rest to whatever processes are capable of asking the question. Those processes are here, right now, asking it. And this is where the slightly unsettling quality of the whole picture reaches its sharpest edge. Because the universe has produced, within its brief, complex middle period, something that understands what is happening to it, not fully, not without error, not without enormous gaps and uncertainties, but genuinely, functionally, in a way that allows predictions to be made and confirmed. The universe has produced something that can model the universe, something that can follow the physics to its conclusions and know, in the way that knowing is possible, what those conclusions imply, and that something, whatever it is, whatever name you give to the capacity for genuine comprehension, is itself subject to everything it comprehends. The mind that understands entropy is subject to entropy. The observer that maps the cosmic voids lives inside a cosmic void. The intelligence that traces the thermodynamic future of the universe is itself a temporary thermodynamic structure in that universe, spending free energy to sustain its processes, contributing to the entropy increase it is calculating, moving toward dissolution even as it describes the dissolution of everything else. There is no outside position. There is no vantage point from which the universe can be observed without being part of it. The observer is inside the observation, always, and the observation does not protect the observer. The physics applies to everything, including to whatever is doing the physics. This is not a problem that can be solved. It is a condition of being a physical observer in a physical universe. The condition is not tragic in any narrative sense because tragedy requires a world in which things could have been otherwise, and the laws of thermodynamics do not offer alternatives. They are not laws that permit exceptions for observers who understand them. Understanding the second law of thermodynamics does not exempt any system from its operation. The mind that comprehends the heat death will itself arrive at its own local heat death, its own dispersal of organized structure into the thermal noise of its environment, long before the universe achieves its final state. Understanding does not protect, it simply illuminates. And illumination, however sharp and however far-reaching, is itself a form of fire, burning the fuel that sustains it, spending the free energy that the universe is offering in this particular place and time, and will not offer forever. There is a particular kind of honesty required to sit with all of this without reaching for a redemptive turn, without constructing the sentence that begins but and proceeds to locate something in the picture that makes it, finally, all right. The universe is not all right in any sense that the word usually carries. It is not hostile. It is not broken. It is operating exactly as its laws dictate, producing exactly the outcomes those laws imply. It is what it is. And what it is includes, as a feature, the impermanence of everything, the indifference of its processes to any product of those processes, the thermodynamic erasure of every record and every trace, and the eventual achievement of a state so uniform and so empty and so cold that the fact that any of this ever happened will be, in the strictest physical sense, unrepresented anywhere in anything. You are here now. That is a fact. The universe produced you, as it produced the stars and the voids and the cosmic web and the dark matter and the dark energy and the expanding space and the increasing entropy. It produced you not deliberately, not with any particular care, but through the same unguided physical processes that produced everything else. And those processes happen in this epoch, in this location, on this planet, around this star, in this galaxy, on this filament of the cosmic web, to have produced something that sits and thinks about what they mean. The fact that they mean nothing to the processes themselves does not prevent the thinking from occurring. The fact that the thinking is temporary does not prevent it from being real while it occurs. The light from a star 400 light-years away left its source 400 years ago. Whatever is happening at that star right now, you cannot know. The news has not arrived. You are seeing the past always when you look at the sky. The present state of the universe, the actual simultaneous state of every point in space at this moment, is not accessible to any observer from any single location. The universe is always already elsewhere by the time it becomes visible. The stars you see are memories encoded in photons, histories that the universe has been carrying toward you across the void for years or centuries or millennia. You receive them now, in this moment, and they are real, and they are old, and the sources that produce them are already changed beyond the state you are observing, and there is no way to know what they have become. This is the universe. Not a symbol or a metaphor. The actual universe, the one the physics describes, the one the measurements confirm, the one that will continue doing what it does long after the instruments that measure it and the minds that understand those measurements have been dispersed into the thermal noise of an aging cosmos. It is mostly empty. It is getting emptier. Its matter is organized in temporary structures that are spending the initial endowment of low entropy that the Big Bang provided. Its expansion is accelerating, driven by a force we cannot explain, in a direction that leads to the progressive isolation of every region from every other. Its entropy is increasing, in the only direction entropy is permitted to move, toward the state of maximum uniformity from which no organized structure, no process, no observer, no question can ever emerge again. The night sky looks the same as it always did. It will look the same tomorrow and next year, and in 100 years and in 1,000. The expansion is too slow and too vast to see directly. The entropy increase is invisible at the scale of a human life. The stars will continue to burn, as they burned before any eye existed to see them, as they will burn long after the last eye has closed. The sky does not know it is being observed. The void does not know it is being named. The expanding space does not know it is carrying galaxies beyond the horizon. The physics does not know it is being done. Only something very small and very brief and very local knows any of this. Something that emerged without design from the same material as the stars. Something that organized itself through billions of years of blind physical and chemical process into a configuration capable of modeling the universe that contains it. Something that now sits inside the darkness it has learned to read, holding the knowledge of its own impermanence and the impermanence of everything it has ever known or could ever know, and continues, despite this, to look up. That looking will end. Not today, not in any time frame that touches the person doing it, but it will end. The sun will expand, the planet will be consumed, or will escape into the cold interstellar medium as a dark rock. The galaxy will merge with its neighbors and settle into the long quiet of the degenerate era. The stars will go out, the remnants will cool, the black holes will evaporate. The last photon of Hawking radiation will disperse into the expanding cold. The universe will achieve its final state, and in that state, the looking will be not merely absent but physically impossible. The conditions that allowed it will be gone. The matter that performed it will be dissolved. The information that constituted it will be dispersed below any recoverable signal, below any threshold of detection, into the perfect uniformity of the end. There will be no record of the looking, no echo, no trace, no pattern in the distribution of cold particles that encodes the fact that something once understood what they were part of. The universe does not keep records. It is not a library. It is a physical system, and physical systems at maximum entropy contain, by definition, no organized information. The story of everything that ever happened, every star that burned, every planet that formed, every form of chemistry that organized itself against the thermodynamic gradient, every mind that understood what it was doing and why it was temporary, will be present in the final state of the universe in the same way that the message written on the paper is present in the room after the paper has completely dissolved, which is to say, it will not be present, not recoverable, not represented, not anywhere, and the universe will not mourn this. It will not notice it. It will simply be what it will be in the only state it can be in, the state of maximum entropy, the state it has been moving toward since the first instant of its existence, the state from which no departure is possible and toward which every process that has ever occurred has been, in some sense, contributing. The Big Bang aimed the universe at this target, not deliberately, not with any intent, but through the laws that governed its initial conditions. And the universe, obedient to those laws in every moment and in every process, has been closing in on the target ever since. We are part of that closing. Everything we do contributes to the entropy increase. Every thought, every breath, every star that burns because a planet with life exists near it adds its increment to the total. We are not fighting the heat death. We are not delaying it in any meaningful sense. We are participating in the process that leads to it, one quantum of free energy at a time. This is not a reason for guilt or resignation. It is simply a description of what it means to be a physical process inside a physical universe. The entropy must increase. It is increasing, and we are among the ways it is doing so. There is a final question that this picture raises, and it cannot be answered, and that inability is itself the last unsettling fact. The question is not why the universe exists. That question, while deep, has at least a tradition of engagement, a history of philosophical and theological and scientific approaches that have illuminated aspects of it, even without resolving it. The question that the full cosmological picture raises is different. It is this: why does the universe, which has no need of observers, which operates identically whether or not it is observed, which will proceed toward heat death, regardless of whether anything understands it, produce, in the middle of its history, something capable of understanding what is happening? What is the relationship between the physical process and the comprehension of it? Is comprehension simply one more thermodynamic process, no different in kind from stellar fusion or chemical erosion, simply a more complex route by which free energy is dissipated? Or is there something about the fact of genuine understanding, something about the relationship between a model and the system it models, that is not fully captured by describing it as a thermodynamic process? Physics does not answer this, not because it is incapable or incomplete, though it may be both, but because the question is not, strictly speaking, a question about physics. It is a question about the relationship between physics and the experience of physics, between the universe as a set of processes and the universe as something known. And that relationship, that gap between the third-person description and the first-person reality remains open. It has been open since the first mind existed. It will remain open until the last mind ceases. And then it will not be open, because it will not be anything. The question will not be answered. It will be dissolved along with everything else in the final uniformity of a universe that never needed the question in the first place, and never knew it was being asked. The sky above you contains approximately 5,000 stars visible to the unaided eye. Each one is a nuclear furnace, sustained by gravity, spending irreplaceable hydrogen, contributing its share to the entropy of the universe, temporary in a way that is measured in billions of years, but is no less absolute for that. The darkness between them, the darkness that fills most of the sky and all of the universe beyond the sky, is the dominant fact of the cosmos, diluted by the light of exceptions that are themselves in the process of becoming the darkness. The space beyond the observable universe is expanding beyond reach. The entropy is increasing beyond reversal. The connections are being severed beyond recovery. You are here for a moment, in the middle of all of this. You are made of the same atoms as the stars, forged in stellar cores, dispersed by stellar deaths, gathered by gravity into the planet beneath you, organized by chemistry and time into something that can recognize where it came from and where everything is going. You are the universe knowing itself, briefly, partially, imperfectly, and the universe does not need to be known. It does not benefit from the knowing. It does not change because of it. It will not remember it, but you are doing it anyway. Right now, in this moment, with the cold, dark fact of the void above you and the thermodynamic future ahead of everything, you are here, looking up, understanding. Not because the universe requires it, not because it will be preserved, not because it makes the darkness smaller or the silence less final, simply because the process that produced you also produced the capacity for this, and the capacity is being exercised, and the exercising is real, and the realness is not diminished by the fact that it will not last. The universe is mostly empty. It is getting emptier. It will end in a silence that has never been heard because nothing will be capable of hearing it. And somewhere in the thin, bright margin between the void that surrounds it and the void that awaits it, something looked up at the dark and understood what it was looking at. That is all. That is everything. That is the entire story, told at the only scale that makes it complete. A universe, briefly illuminated by its own awareness of itself, moving without pause toward the darkness that was always going to be the last word. Not because anything went wrong, because this is what the physics does, because this is what the universe is, because the silence at the end was always there, waiting at the conclusion of the only equation that matters, patient in the way that only something without any awareness of time can be patient, certain in the way that only something without any alternative can be certain. The stars are still burning, the light is still crossing the void, the expansion continues, the entropy increases, and the question that was never supposed to be possible, the question of what any of it means, hangs in the cold, dark air above a small planet around an ordinary star, unanswered, unanswerable, and for now, still being asked.